Hörst du mich? Hörst du mich? Da sind auch die anderen da drin. Also, hört er mich? Ja. Aha. Hörst du mich, wenn ich jetzt spreche? Ja. Also jetzt hörst du mich sozusagen, wenn ich spreche. Okay. Also hier in Deutschland hört man mich. Okay. Ja. Aha. Kann, aber ich sehe euch nicht, ne? Da steht C, Gaio, Vinicius, Pontes, Korea. Also jetzt sind schon der Farhan Hussein, der Donny, der Alexander Adamczyk, Florian Gerber, Bonnet, sorry, von euch, die Patrice ist dabei, eine Thais Arroyo ist dabei. Okay. Ciao, ciao. Tschüss. Bis gleich. Wenn es nicht klappt, dann lass mich sprechen von dem Handy, ne? Adiós. 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 Adiós.
Right now, can listen to Professor Aneziris. We are just checking out the sound for
Yes. Yes, I'm hearing you. I'm hearing you. Do you hear me?
Yes, we can hear.
Okay, excellent.
Okay, so everything checking. Good second. Oh,
Okay, so
Essa não usa. As pessoas vão estar mais tratadas assim, porque tá. Porque pelo menos acho que dá para curso. A gente faz tira mais um quadro da vida. É, e tem também aqui. É, mas tá pegando. Tá pegando. E o áudio tá pegando mais sistema. A gente não vai conversar. Se não for microfone, ele está falando um pezinho. A gente tem que falar para ensinar bem. Tá, expresso. Certo, entendeu? Não vou testar umas coisas que vão ficar aqui, elas vão ser só por exterior. Essa combinação. É, que eu acho que vai ficar mais. Sim, pode ser. Acho que as só que vai se focar. Assim, eu só vai na frente. Deixa eu ver se. Falar fazendo a bagaça. Só também isso aqui, pessoal. Pode ver que está aqui. Sabendo que eu não me. Tá. Vamos lá. Melhor, né? A luz daqui do que essa. Eu acho. Já é bom. Ele gosta da coisa. Eu não, mas. Eu não sei. Wow, it's muito e a luz tá bom, né? Bem, outra não. Mas não é. Sabe, não é. Deixa ser. Aí a transmissão. Nesse momento, ninguém está na cara. Acho que não sabe. I think we are ready now.
Yes.
If you'd like to open the session, it's the status.
I do not see you, no? I see only your name.
My students. Okay, guys. This is
Okay.
we won't cover it, but it's going to show only me, probably. But in the transmission, the YouTube, maybe we can send the link. We have two cameras in the room, so be able to see the presenter and the audience. Yes.
Sounds good. So first of all, I would like to thank you, all of you in Brazil, especially the whole team of Professor for organizing this very nice workshop. I saw you now and I say hello. So Victor, thank you very, very much. It's a great opportunity that before the UNITSA in Mexico, that my group meets your group meets our group, and makes refractories again firing. And as a response to the global climate and energy changes, the sustainable trip to Ithaca is the main topic of our workshop, Green Refractories. Is it a vision or a friction? And I believe it's a vision. And for basic science and for all industries, in particular for the refractory sector, it's one very interesting question. But also a challenge for the young generations. And our discipline deals with sustainable materials for high tension processing, as well as with sustainable processing of high tension materials. And UNITSA, as it's going to be, or also in the past, especially also the group of Professor Pandofelli, offer a unique opportunity for our materials not only to be used as hidden heroes, but to show to the world that we can successfully meet the challenges with our materials, with refractories. Everything is flowing, tapandari, as Heraclitus mentioned 2,500 years ago. But keep please in mind, not only one way will bring us to the solution. More different combinations of firing, different combinations of material, composite smart material system, supported by computational design, will provide the answers for these emerging and challenging topics. Once again, great thanks to everybody of you and all the best for today. And I give the word to Victor, to Professor Pandofelli.
Okay, I don't know whether is it okay?
Yeah,
When? Okay.
everything is fine.
Okay. Thank you, of course, for this is for it's a pleasure to have this joint meeting. Uh, we had we had fun yesterday, and we hope that we're going to have also today. Of course, that this morning we have the technical sessions, and afterwards we're going to have a sightseeing to one of the regions of our place. But I think that today is going to be very important because we can share our vision about the present and future of the refractory area. Then, trying to follow our schedule, the first talk that we're going to today is from Dr. Patrick, and we will present the title of the talk. And the first one going to be recycling of magnetic carbon for raw materials, energy, and climate efficient in high temperature process. Welcome, Dr. Patrick, and you have 5 minutes for presentation. It's better 15, 5 per question.
Okay, just before you start, that's what I like that we already published the link of this streaming in the chat. So if you want to have the cameras and all the stuff, you can see the screen there. The audience, please access the link we just posted in chat. Okay, thank you.
Okay, correct. Is 30 minutes, then 25 for the presentation, some time for questions, but feel free, as long as it's in 30 minutes.
I will do my best. So thank you very much, Professor Victor, for this invitation. Thank you very much to your whole crew for the hospitality. And yeah, we have a great time, and it's very important to have this exchange. And now I would like to take the opportunity, because we are here in the framework of the research training group 2A02, and we would like to present you a little bit or give you an insight of what we are doing in this research training group. What is our research training group? On the one hand, let's say, I will call it social background, and on the other hand, the technical background, when we really go into the subject of refractories and what is the need for refractories in the future. So there was, before, or when we came for this research training group, there was a social motivation, more or less motivated, especially in Germany, but could also be in other countries in the world, that we have a lack of qualified personnel. We can call it human resources, especially in Germany. We have a lack of these qualified personnel, especially when you think about the amount of engineers which will retire in the next 10 years. We need to replace them by new students, and not only by students, but by qualified personnel, because they work in very crucial industries in steel sector and aluminum sector, which are very important for the society, and not only in Germany but also all over the world. So qualified personnel, but they don't get burned. You need to have a comprehensive education for them. You need to train them, of course. And this is one part of the research training group. And the other one is that we have a need for environmental sustainability. That means the natural resources. We need to take care of the natural resources we have. We need to focus on recycling, on materials. This is just a general overview. We need to develop new materials. Our subject, of course, much more performance materials. We need to increase the materials life cycle to resave the raw materials, and also need to develop a new process with that a higher efficiency. Other source of power, for example. Just these 2 minutes. And it means we have a responsibility for the future generation, not only from the point of view, but also from the society point of view. That's why we need, or the objectives in the research training group is that we have an interdisciplinary structured training of doctoral students in the field of recycling and upcycling of factory materials. So on the one hand, it's a training, on the other hand, on a really new and important topic in the field of the factories. So what switching the theory and practice, as we always do in the field of the factories? Yes, we need to use a lot of basic science, material science for the factories, but always have in mind that we need to apply it in the steelwork, for example. We need to apply it in the aluminum industry. So this is very important. So we need to link fundamental research to focus on industrial processes, that we can convert our findings into the industry to be used there. Sorry. And of course, this is very important, interdisciplinarity. So we are material scientists, but we also are process engineers. But this we need. We need now computational science, for example. We need physics. We need maybe biologies when we thought about renewable binders, for example. So we need the knowledge from different disciplines, and this is something you cannot learn during your studies because you're focused on a specific subject. For example, in Freiberg, we focus on material science, but with focus on
ceramics focus on glass and construction materials and how to process them, but we are not able to learn our students how they can model, for example. And on the other hand, you need to learn this during your PhD. This is something you have to implement and to support your PhDs, and of course internationally. 10 years ago, it was not, or let's say this was a new topic, but now I find that you have, so that's like become in the institute, but also in the relationship, it's internationally, like we have it today. So we cooperate with, we can call them colleagues and friends all over the world, having focus on one subject, it's refractories, of course, different point of views, and especially one guy can work on refractories for 20 years, maybe on a steel ladle, but on one hand, the one guy is working on porous plugs and also the castables and how you try the castables, and the other one is learning, or let's say, try to get into the corrosion of carbon bonded refractories, more or less the lining and how it will impact the steel cleanliness. So we are working on the same topic, but maybe not on, or let's say, getting too much into networking. But we also need all the same basic strengths, and that's why we need to interconnect. That's when we need to talk, and especially this internationality is quite important. So it doesn't matter, or let's say science doesn't matter where you're from, and it doesn't matter which cultural background you have. All which interconnects us is, let's say, we need to focus on rules like good scientific practice by DFG, so that are rules that you will follow. Otherwise, science can cross borders and you can work with everybody over the world. But let's say keep the rules like good scientific practice, and then scientists can cross all the borders. Okay. This is our team, research training groups. So we have 2 funding periods. First funding period started in 2022 for 5 years, and then we call it cohorts. This means we have, let's say, 12 sub-projects in this research training group. The first 12 sub-projects started in 2022 with 12 PhDs, and after 2 years, the second cohort started, which means we have another 12 PhDs, and now we are at 24 PhD positions working in this research training group, and we would like to claim for a second funding period after 2027, and then we will have a third cohort, of course. Then the first cohort will graduate after 4 years, being doctors, and then we have another, let's say, 24 PhDs working in parallel for a couple of years. So at the end, we will have 36 PhDs in the whole project, 4 years contracts and full-time jobs. So they can really focus on these topics we are, let's say, focusing on the research training group, but it's not only, I will show you in the next slides, not only from scientific point of view, but also soft skills we need to check. This is an image of now our PhD students and the PIs in research training group. So we need, or let's say, by this research training group, we are able to have different tools. So we can establish, by the funding of the DFG, optimal framework conditions, and especially a motivated environment by the professors, by the PIs, to support the doctoral students and to promote an interactive and stimulating working style. This is very important for our PhDs, since they are not on their own, but they can interact, and I guess really well. So we have, on the one hand, also a self-organization of the PhDs within our research training group, and we have 2 representatives, for example, which will be elected every 2 years in an executive board and steering board. We have regular interaction, supervisors and mentors, which is of course very important. Internships abroad, I will focus on the next slides. Industrial placements, of course, very important. And practice-related feedback by members of the industrial advisory board. So we have an industrial advisory board that ensures that the students, as I told you, we are say industry related sets, they are on the line, let's say something like this, and maybe their research is also very practical. So at the end, we have a holistic qualification of the PhD students. So they need hard and soft skills because this is something they do not learn during their studies. When they are finished their graduation, master or diploma, then they have also a lack of soft skills and need to train. Yeah, it's a matter of how it's a person. So there are persons which are very good in interconnection and in talking to each other, but a lot of people are shy, and you need to train them to interact with other people, overcome their shy, and go into discussion with other researchers, and making some connections, especially for their career and also in the scientific or industrial sector. It's very important, and this is like Switzerland tool name, I would say. The tools we are using to research training groups. So we, of course, it's quite clear, attending a conference for our PhDs. We have a lot of invited lectures. There are PhD colloquia, general meetings, summer schools, and autumn schools like we're here in Brazil at Oscar. We have workshops, field trips, and also specialized soft skills workshops. So I would like to focus them on the next slides. So, yeah, as I told you, we started in 2022, and especially we had already some presentations, a couple of presentations at the United States in 2023 in Frankfurt at the Freiberg Factory Forum 2023, 2024. So we had a special poster seminar where our PhDs need to create a poster with their state of the not state of the art, but the state of the doctoral, and need to defend them against the visitors or the attendees of the factory forums and get into interaction with them. You need to defend their research on the posters. We were at the Refractories in Prague to present our research training group with the ICR. In Aachen, the annual meeting of the German Ceramics Society in 2024, and also at the ESAS 2025, and there will be also a couple of presentations at the United States in 2025. So our PhD students, of course, need to learn how they will prepare a presentation and giving a presentation, and also present them and defend them as a discussion part. This is very important for scientists. And we have also a lot of invited lectures with different topics from well-known researchers all over the world, like Professor Giorgia Franchi from Padua in Italy, which she's focusing on 3D printing, for example, of ceramics. For example, we have Professor Stemahan from USA. We have Professor Yachi Dai from Wuhan University of Science and Technology in China, Professor Andrzej Jankowski from Prague University in Czech. Professor Ino Chung, for example, from Seoul, Korea, who will be giving a lecture about fact safes, so thermodynamic calculation. Dr. Acker from ArcelorMittal, from a point of view how steelwork is facing the new transition from a general steel production to a way of direct reduced iron production of steel, for example. But it's quite important to have these professions, and that our students can listen to them, learn, and also get also into touch with them and getting networking. Summer schools and autumn schools, so we had the opportunity in 2023 to visit Tata Steel in the Netherlands during the summer school, the autumn school at the university at Padua in 2024 with the group in Italy. Here we have an image where we are in this very traditional let's say famous room in the University of Padua, and also some months ago we were at the ESAS Fire School in 2025 and based at the IPATS, for example. PhD workshops, it's quite important. As I told you, we came from different disciplines, and so from physics, okay, most of them are material scientists, but on the one hand they just focus on modeling, the other ones focus on spark plasma sintering, for example, aluminum industry, steel industry, and then they need to learn from each other what they are doing, for example. And therefore, we have these PhD workshops. So every PhD need to organize a workshop, present very briefly in, let's say, 10 to 15 minutes, the scientific background, what they are doing, and presenting, and also what they are doing in the lab, for example. So presenting spark plasma sintering. In the middle, we have the casting of steel, for example, to get an insight of the interaction of slag with steel for the refractories, and also in the producing ceramics on the right-hand side. So up to now, we have 50 colloquium from November 2022 to September 2025 now, and now a new cohort. So we have the first 3 colloquia from the new cohort, now new PhDs, which are now starting their PhD 7 months ago. So also general workshops like FactSage training course, FactSage application workshop, workshop about research data management, which is really important that you need to secure these the data and how you manage data, that it's could be after the FAIR principle, could be accessible by everyone. Maybe you need these know this guy and that's side. So Otávio was at our institute in internship, for example, and listened to this. I guess it was FactSage workshop. Okay, so it's quite important to train our students for these special workshops and, or let's say, general workshops. Field trips are important so that we get into touch with the industry, for example. So we are able to visit Ferrari steelwork, for example, in Riesa, which is located very near to Freiberg. We were at Refractories, it's a company which focuses on recycling of refractories and preparing the recycled refractories. Refractory steel, which focuses on producing from these recyclates some industrial refractories for steel, especially. We were at the Ceramic, which is fair trade for the worldwide fair trade for ceramics, which takes part every, I guess, 3 or 4 years in Munich, where the whole ceramic industry will meet at the fair trade. We were at treatment aluminium in Essen in Germany, so an aluminium producer, for example, and in a couple of power research. So that our students get in touch with the producers and see what processes. So especially when they came from the physics, for example, they never have been in the industry, and now they know where their materials will be applied. They are, and of course, a lot of soft skill workshops, like especially related to women. This that was given that women lead differently to get focused on that. We have by Diana as a former ATM president and professional development for engineering PhD students, especially to using networks and interconnect professions, for example. And there was also a soft skill workshop for open science and open access publication, which of course important. You need to publicate, especially when you are a student. When you begin to study, you learn how to read a scientific book. When you do your master thesis, you learn how to read a paper, and 1 year later, maybe you need to write your own paper. And that's a real progress and like pushing into cold water, and you need to focus on also open science and open access publication, which is very important. So you need to train in this. Very important, ensuring good scientific practice. This was also a workshop how you can ensure good scientific practice. Team communication is also very important to learn, especially work in an environment with different, not only different people, but also different culture background and so on, but all with the same focus. Okay, just an overview of the some stay abroad and this industrial internship, for example, with Matteo at the university in Japan. Alexander was at Kosaki Rima in Japan, visiting a lot of steelworks in Germany, Europe, Central Asia, And you see it on the maps, and also Yishin was at Virginia Tech in the USA, for example, Borges was at the University of Ottawa. So they, really interconnect with their, let's say, with their supporters and supervisors in the MgO industry, and get out of their comfort zone. It's call it like this. And there's also really important supervision system. So I get this image from YouTube sometimes. So it's like the situation in the US universe. So the student carries the whole thing, the teacher is sleeping, and the university gets the money. The students, this is, let's say, something like a funny thing, how it's a situation in the American university, but we have like 4 columns which supported our PhD. So, for example, supervision of Yishnu, of course, he has a university supervisor A, which is in his case Professor Kiefer, and another supervisor from a different field, of course, also an engineer from Professor Fiebach. He's focusing on the interdisciplinarity and social skills. And then he's supported by a mentor from the Industrial Advisory Board. In this case, it's by Bruno Bocchini working at Tata Steel. He gave him practice related feedback and also support the networking skills of him. And there's also a second advisor from a MgO university, in this case, Professor Seidel from Virginia Tech. He also visited him. And he supported this internationally networking and also the language skills. So 4 different columns will support the PhD of Yishnu in this case, and this is the case for all of our students. And they are able to choose and get into contact with their own mentor. So in the beginning, of course, they will be supported, but they choose their own mentor, not only from the industrial advising, but also from the MgO industry university, and get into contact with them. Okay, this was the social motivation to train new students, but of course they work at a specific field. This is a technical motivation. Technical motivation is about the recycling or upcycling of factories. So worldwide, approximately 2 billion tons of steel will be produced every year, and you know, for 1 ton of steel you need approximately 2.5 kilograms of MgO-C. That means every year you get a huge quantity of consuming factories. And for now, further life of these useful factories, most of them are deposited on landfills, which is great cost at the worst carbon footprint. So it's the worst thing you can do. You have very often also a downcycling, means an application for any sectors like aggregates for the road construction, and yes, recycling. Just today there are some projects, let's say products which use recycled materials, but it's still at a rather subordinary role. And the technical motivation of the research training focus here increase the research potential for the application of the refractory recyclates. In the mean of recycling, that means similar application fields. So you have MgO-C, recycled MgO-C from the label, and use it again in a label, for example. And there's also upcycling, that you use the recycled MgO-C and produce new materials for new application fields, sometimes with a higher value. This is the upcycling material. So we have 2 core ideas, like especially, as I told you, for every cohort we have 12 PhDs, 6 PhDs focus on the core idea recycling, which is the objective overall increasing the recycling rate of MgO-C and develop environmentally friendly binders and factors. We will hear a presentation by Daniel later on this topic. So we have MgO-C recyclates and also environmentally friendly binders. They are resin and pitch free and produce new bricks for steel ladies. And of course, there's a lot of issues you need to handle. And the second core idea we're following is upcycling. It means that you open a new application field of MgO-C recyclates, and in this case, we would like to develop a solid material ceramic composites by pre-treated MgO-C recyclates and mix them with steel powders to produce electrodes for the aluminium fused soil electrolysis. So these are the, let's say, PhD topics they are working on. And today I would like to focus the last minutes on the upcycling. I guess I have just 5 minutes, 10 minutes left. Yeah, so I speed up. So focus on upcycling. So aluminum is extensively utilized in the various areas of modern engineering, and for producing 1 ton of primary aluminum generates about 9 tons of CO2. On the one hand, for the electricity production, and also additional 1.5 tons of CO2 by these consumated graphite electrodes, which are used today. And we would like to increase the intention to develop ceramic, ceramic, and metallic phenol anodes. This is, of course, not a new field. So there are researchers working for 20, 30 years about this, let's say, phenol electrode anodes. And there's also, let's say, if you have a look on this diagram, you have electric conductivity on the left-hand side. It's a very high electric conductivity are the metals, but they have a very poor corrosion resistance in this aluminum field. And then you have a field of ceramic, which has a very high corrosion resistance, but of course a very low electrical conductivity that they cannot serve as anode. And in the middle between, it's our this is the situation now. And we would like to increase, or let's say add new materials to this diagram, for example. So what we are doing now is we're getting these MgO-C recyclates from the steel industry after they were served, and seeds them to, let's say, there are different recyclates we used on our study 0 to 1 millimeters, and seeding them up to minus or below 125 micrometers. In this case, ceramicsthrough contain about 20% of carbon. Of course, we need to get rid of the carbon by burning out. This is a thing we can discuss about. Of course, yes, we would like to reduce the CO2 emission, and now we get MgO-C recyclates and burn out the carbon, which produce definitely CO2. But you need to focus on or let's say compare it. When you start with new MgO to produce these ceramics, you need to have this process to get out CO2 out of the magnesium carbonate, and this amount is much higher. So you will produce less CO2 when you use recyclates, MgO-C, and burn out the carbon instead of using new MgO from the magnesium carbonate. This is something can see. Okay, and then we have MgO, and we use 40% of this MgO and mix them with new stainless steel. Here's the composition of the stainless steel: is a chromium nickel, molybdenum steel, and then we mix it in an Irish mixer with fructose syrup and deionized water to get a granulation. And from these granulates, we dry them, dividing them in air, of course. And then sinterate these granulates in argon for 2 hours at 250 degrees, and at the end, seeding them to different classifications. So this is our pre-produced granulates of these ceramic matrix composite, for example. And then we use these different granulates, mixing them in a different share, and produce by cold-isostatic pressing these electrode samples. For example, of the electrode samples again need to debine because they were processed by these silk pressing, sintering them in the air, and at the end we need, and this is the point of view, to get a higher corrosion resistance, and this is one objective of the research, pre-oxidation. So now it's in the metal state, and we need to pre-oxidation at different temperatures, for example, which was the objective research 800, 900, 1000 degrees. For example, CT image microstructure. So we see that it works, so the process is well controlled, and you see after 900, 1000 degrees, so like a shiny surface on top. These are new oxidized surface. You can analyze it. So in the acid state, you have a mixture of blue is the steel and red is the MgO, and after increasing the temperature, so pre-oxidation, you have oxide after 800 degrees formed around the steel grains. If you increase the pre-oxidation temperature, you form new iron oxide layers, new phases, and especially at 1000 degrees, nearly a complete reaction of the MgO with say steel forming new spears, for example. So something happens during this pre-oxidation, but we like to focus on especially electrical conductivity. So you have the electrical conductivity of carbon-based anodes like carbon graphite, for example, and recrystallized silicon carbide. And you see that our sintered materials, so the mixture of MgO and steel, are in the range of graphite. So it works as an anode, and even after pre-oxidation, 800 900 degrees, our composite material are in the range of carbon. So even after pre-oxidation, they work quite well. But we need this pre-oxidation to increase the corrosion resistance. So that means, yeah, we have an electrical conductivity. It's signed diagram, but we are not sure what is the corrosion resistance. So it's like a bar. We are not quite sure. We need to test the corrosion resistance of our materials. And we started first of all with the sintered material, so 41% MgO, 31% steel in stein cell at the temperature 1000 degrees, 2 hours, with cryolite, for example. This is from the whole Howell process. And at the end, we get the material and can analyze this. So during this corrosion resistance, the cell was quite stable, so it works as an anode. And afterwards, the sample was cut in the lowest side, and then we analyzed it in different states. So the outside, I don't want to focus on this in great manner, in a little bit away from the outside and in the middle. We also saw, for example, here we have fluorine in the middle, so here in the S-sintered state, the cryolite completely diffuses into the material. Just to conclude, so we were able to produce composite materials in an S-sintered state which exhibit sufficient electrical conductivity but show aggressive cryolite attack in MgO grades. And we need, or found that we need to pre-oxidize the surface. So the electrical conductivity is lower but quite sufficient, and the corrosion resistance will be promising. So we are on this next investigation. This is a part of Sarah Jaroszewski and Patrycja Kaiser's focusing on the pre-oxidation experiments. So she found that the furnace type can influence the oxide composition, structure, and these protective functions pre-oxidize. So different techniques, like this microwave plasma burner, electrical resistance furnace, gas fires furnace, for example. So different atmospheres try to keep it on the same level, but you see that some technologies has a higher rate of heating and a much higher rate of cooling, especially in the case of microwave plasma furnace. And you see it at sintered state that the different pre-oxidation processes at 900 degrees result in a different mass gain. The mass gain, of course, is the oxidation of steel, and we see a different degree on the mass state. We see a different different condition of the surface, for example, and a different state of oxidation. So some parts just oxidize in the surface, the others show completely oxidation through the whole diameter, for example. And Patrycja will focus in the next time on investigating the corrosion resistance of these different surfaces treated by gas furnace, electric furnace, for example. And she was able to show that the microwave plasma furnace leads to enhanced formation of chromium-based compounds, for example, and show no distinct surface oxide layer. And it's important to have a precise evaluation of the efficiency in terms of corrosion resistance, which is still pending. And of course, in these 4 SI2, there are, as I told you, 6 PhDs or now 12 PhDs working with this topic. So they are focused on a microstructure designed by FAST and SPS technology, focus on the Raman spectroscopy of MgO-C, investigated inner adults for the aluminum mold salt electrolyzers, investigation of the oxidation resistance, and zone mechanic properties of materials. So this brings me to the end. Would like to summarize. So we would like to develop a new environment-friendly materials, call it smart refractories. This is the future of the refractory industry. So we need smart refractories, and to produce smart refractories, we need smart refractory engineers, and we need to train them. So holistic education necessary, which was able by the TFG funding. In this research training group, we have a professional development of advanced training, field trips, internships involvement of the PhD students in decision-making processes, coaching and supporting them, and also have team-building activities. And I would like to end with the statement of Einstein. So education is not the learning of facts, but the training of the mind to seek. So this is important, getting a smart engineer. So we'd like to thank the German Research Foundation on this project, and thank you very much for your attention.
Thank you very much, Dr. Patrick, for the clear explanation about the project and the current research and or the thermal channels and recycle. We have time just for one questions, and I would like to ask the question. We know that the research about ethanol has been going on for quite a long time. I remember the time that I was working partially this project in Alcoa, and it lasted some 25 years. It takes it to work, and they gave up. What do we think that are the novels nowadays that are promising carried out in this idea? Of course, the pressure of the climate situation is clear and stronger than in the past, but the challenges are there.
Yes, yes, indeed. So one, you need to state that you are not able to catch up, or the PhDs are not able to catch up with developers of inert anodes of 25 years. And this is not what they would like to do. They would not like to revolute these projects. So on the one hand, they would like to focus on the education, and on the other hand, on the development of new inert anodes. But they cannot catch up with development of 25 years. This is quite clear because other groups has much more knowledge in this field. But we are very promising, or let's say we have very promising approaches that when you know you have the ceramics or the metallic inert anodes, for example. And it's quite promising then when you mix these MgO with steel, not only to get inert anodes, maybe not from an electrical point of view, such a good performance, but the corrosion resistance is very well, especially against cryolite attack. And we see maybe with these new, let's say, approach of pre-oxidation, having a good technology of pre-oxidation, the perfect temperature of pre-oxidation, we can have a very good contribution to develop new inert anodes. Of course, not inert anodes because they will also be consumed over the time, but let's say general inert.
Thank you very much.
You're welcome.
So the second call, now Dr. Otávio Borges, that is going to present design for ceramics through Kirkendall and dealloying-like mechanisms to include high-temperature thermal insulation.
Thank you for introducing me. Thank you very much. It's a pleasure to be here today presenting this work. And it has been a really good time with people from Fiverr. We can think about other collaborations and other visits from our side. But now I would like to start my presentation with historical data, because I would like to talk about Dr. Spencer Silver, which was a young researcher in 3M during the 70s. And one of his main tasks was he was hired to develop a super glue that could stuck with everything and make everything stronger. And after 5 years of study, he was able to synthesize an adhesive that just stuck slightly on the surface of papers. So at this point, he failed miserably in producing this super glue. But after some years, they realized that having such adhesive that just slightly stay, just slightly adhesive in the paper, it will be interesting because now we can have notes and 3M starts to sell post-its. So the idea initially was a failed idea, a wrong idea, it did not work, but after some time they realized that it could be even better. And why I'm talking about this? Because in our research, sometimes it works like this. We have some bad results and we blame ourselves, oh my god, we have bad results. But sometimes we need to make eliminate with the lines. We need to look at other perspective and try to see value of that behavior for another application, for another type of property. And this was the case here, talking about design of thermal insulators. And but before I give you too much spoilers, let's understand our motivation. Well, we all know that industries play a central role in the carbon emission. So one third of all carbon emission comes from industry, and especially high temperature industries. So here we have steel, it's not working, but steel and cement will be responsible for massive production of CO2, and these greenhouse emissions is highly demanding for the environment, right? And if we look at these two sectors, the iron and the cement, because they operate at high temperatures, a huge amount of energy and a huge amount of carbon is related to the heating process, to increase the temperature, to keep the temperature at a high level. And why this relates with, how it relates with refractories, because almost 15% of all energy being put in our process to carry out the process we want to do is lost through the walls, through the store, etc. So if we could design a better insulator to halt the heat transference here, we could have a process with higher efficiency and protecting the environment, avoiding so much carbon emission. Okay, but how to develop some type of insulator? To understand how to design and to produce a better insulator, we need to understand the heat transference phenomenon. And we know that materials can transport heat through three different phenomena. One is conduction, which is the transmission of vibration of the lattice, crystalline or amorphous one. And it will be very important for thermal conductivity at low temperatures. We also have convection, which is related to the mass flux inside a medium. So on top of having the heat transference, we also have the mass transference. And this will be important for pores, for larger pores, structures with pores that are larger than 100 micrometers. And we have radiation. And radiation will be the major contributor at higher temperatures because radiation emitted at high temperatures will be much more intense. It depends on the temperature rise to the fourth hour. And for high temperature applications, radiation will be the most important phenomena dictating the thermal conductivity of the sample. And using this knowledge, our group in previous work were able to calculate using some simulations how the ore diameter will affect the thermal conductivity at higher temperatures. And with this data, we can target an ideal microstructure for a high temperature material, high temperature insulator. So we need to have low intrinsic conductivity, so the dense phase here of my core structure should have a low inherent thermal conductivity, and I need to have refractory phase because it's a refractory, it's designed for a high temperature with a high volume of pores because we want to spread the vibrations of the phonos, and also the important part here is that we need to have pores ranging from 0.5 to 3 micrometers. Why this size range? Because this size range interacts better with the thermal radiation emitted at high temperatures, and then I can decrease the effect of the heat transference by radiation. Okay, so nice. All this background, all this knowledge help us to define a target. Now we just need to process and obtain this type of microstructure. But it's not that easy. We have a trade-off between porosity and pore size. Most part of the time, using the rectangle method, the template method, or even direct foaming, have this type of trade-off. If you want higher porosity, you usually get high average pore size. And then it's hard to have high volume of pores with the ideal pore size range. Well, there are several studies trying to cope with that, proposing other type of foaming agents, other type of setting agents, trying to avoid aging phenomena, and so on. But it's usually hard to get this region, and we need to overcome this issue, break this trade-off, and get higher porosity with the controlled pore size. You don't want nanometer size, pore size. We are targeting in this range of 0.5 to 3 micrometers. Okay, but talking about this production, we usually think the producing method of any kind of material as for information. So I will use different techniques. I mentioned the replica, template, and direct foaming. I will produce my material, consolidate, powder, and then we usually think that we are going to apply heat, and I will get a consolidated body from a particulate body, right? And this is right, this is the case, with all that phenomena we already know, the sintering process, and so on. And we usually study sintering process of one component, one phase only, but most part of time in our research, in our applications, we have more than one phase. So we don't have the sintering of a monophase system. I have the sintering of a multi-phase system. And this will have some implications. Well, if we take a look at one boundary of these two phases, and here I'm just thinking about two phases, you could have any phases, the amount of phases you want. But just thinking about two phases reacting, we have phase X, phase Y, and depending on the diffusion of the ions in this interface and how they will diffuse, if it will be a lattice diffusion, vapor diffusion, and so on, we'll have difference. Usually these diffusions are different, and because of these differences, we'll have the formation of layers with different sizes related to the R and the X and Y interfaces. For example, in the case of alumina and MgO, this is a very classical example. This reaction follows the Wagner mechanism, in which we have an ambipolar fusion, in which the charge neutrality will be ensured by the differences in the diffusion coefficient. So will also have 3 MgO ions come from MgO to alumina and 2 alumina ions from alumina to MgO. And if we take the reactions at the boundaries, we'll see that always I'll have 3 spinel being formed at alumina interface and 1 on the MgO interface. Nice. Up to this point, nothing so new. But some years ago, we started to study the alumina zinc oxide spinel, so zinc aluminate spinel, and we will get it from the reaction between alumina and CNO. And this type of reaction do not follow the Wagner mechanism, but the Brownson mechanism. And now we don't need to have the electroneutrality from the diffusion rates Rather than this, we have electrons migrating, we have oxygen vacancies, and so on. And because of that, we'll have an almost unidirectional diffusion of the ZNO to aluminum, creating this type of voltage. Sometimes we see in the alumina particles, leaving some voidings after the process, because one of the material where the zinc oxide migrates to form the guide and will leave the port. And up to this point, we think, wow, but why is it important? He started talking about polymers, and now we're talking about diffusion. Why does this matter? And well, when we started this study, introducing ZNO in alumina-based castables, we saw exactly this. We saw formation of granite coating around the alumina aggregates, and we saw a lot of voids, pores, causing almost some places the deattachment of the aggregate, the alumina aggregate from the matrix. And this was very bad because, of course, the thermal shock damage resistance was higher, but the mechanical properties usually was very, very low. Because that's why we said, well, we can use zinc oxide in alumina castables, but with some limitations. We need to design the size, we need to be careful about the amount in order to prevent this deattachment. But this was what we saw at that time. But looking at the literature, we can see that other researchers publishing in Nature Materials found another application for this phenomenon, spore generation. They create nanotubes, ceramic nanotubes made out of spinel, zinc alumina spinel. And how they do it? They produce a ZNO wire, they cover this wire with aluminum, and then they fire it to produce the zinc oxide. This way I can have a tube with a hollow tube with nano size. So we start wondering, why not use the same effect for generation to create the thermoinsulators with the microstructure we want, with that size, 0.5 to 3 micrometers. So the idea is, if I have the ZNO, my microstructure, during the sintering, I will have the pore size of that raw material, the zinc raw material. And interestingly, the commercial zinc oxide, zinc powder production of this oxide leads to particles with very thin particle size, very narrow and small particle size distribution, close to that target we had, so close to 0.7, and we were talking about 0.5 to 3. So why not to try it? Why not to design this novel material? This novel insulator is designed for size created by in situ reaction. So, in the first set of experimentals I would like to show you, we designed 3 compositions. One called A-dense, it's alumina, it's our reference, so dense alumina, 1% of destrin, just to make it easy to press, some pressing samples. We have a sacrifice, so aluminum with an agent, a porous agent. So we are going using also as reference in alumina, porous alumina produced by the sacrificial method. And our material, we are proposing the in-situ formation course, which has stoichiometric gamma. So 5% of alumina, 44 of calcite, of zinc oxide, and the destrin. This material follows the same processing route, so we homogenize it, ball milling, then add water and oleic acid, sieving just to prevent any type of different regions, and then press at 100 megapascal. And after that, firing 500 degrees C for 5 hours in open atmosphere. Okay, so let's see the results. As expected, in here we always have microstructure and pore size distribution, in which we use mercury intrusion porosimetry, and also another technique derived from the BET, in which we use nitrogen to account for small pore sizes, nanometer pore sizes. So here we have both techniques together. For the dense aluminum, as expected, we saw dense microstructure with some pores formed at the 3 joints here of the grains. So because we did not have enough energy to obtain a completely synthesized microstructure, so the pores are very thin, 0.1 micrometer, and they are not so, the amount of these pores are relatively low. For the sacrificial one, as expected, we have big pores. The size of the sacrificial materials, the sacrificial additive, was close to 15 micrometers. So we have pores in this range, and also we can see some windows, which is also expected by this method. These windows will make the pores open, and that's why convection here could add more than if it's expected in a completely closed pore. And finally, our new material with stoichiometric aligned, we could obtain the desired pore size, so 0.5 micrometers, and the pores were very well distributed at the matrix, tire material. First, they are open, but because they are so small, we do not expect any effect or minor effects of convection. So let us see the fraction of porosity. I mentioned that the material need to have the right pore size distribution, but also a high amount of pores. And as expected, the dense aluminum did not have too much porosity. The porous aluminum produced by the sacrificial template had 60% of pores, which was expected because it was the amount of porous additive we added. And our material, with pores produced in there just by the Kirkendall effect, the porosity leaved by the reaction, has just 30% of pores. So the porosity is not that good. It's still low porosity for a commercial and feasible thermal insulator. But this amount, 30%, of course, it has an explanation. This occurs because to produce the granite, we were using equimolar mixtures of zinc oxide and aluminum. And if we make the calculations, we will see that in the system, zinc oxides account for approximately 36 volume%. So 36 is the maximum amount of pores I can generate by Kirkendall effect in this system, considering equimolar stoichiometric aligned formation. Okay, so it is kind of a limitation. We can search for other spinels, or we can try to make in a non-equimolar spinels and so on. But there is another way to overcome this challenge. So we start to search for ways to overcome this challenge, and we ask ourselves, well, how are metallurgists producing porous metals? Can we have some idea from their work? And we saw that for metals, they have what they call the alloying method. There are several ways to carry out the alloy in this system, but all of these ways they use the same principle, which is the removing of less stable atoms from a solid solution. And in our case, we had our solid solution was zinc oxide and aluminum together, and have granite. And if we use fat sage, we can see that this decomposition of granite will take place just above 2000 degrees Celsius. It's not feasible, and which is good because we usually use granite as a refractory material. But for our experience, granite was sensible to carbon-containing atmosphere. So somehow maybe reducing atmosphere can foster and anticipate this reaction. So we went to fact stage and calculated again. putting carbon in contact with the granite, and we can see that this decomposition leading to solid aluminum from granite with zinc volatilizing, it will occur close to 1100 degrees C. So much feasible way to produce this type of material. So the idea was producing the pores by the Kirkendall effect during the reaction from aluminum and ZNO, produce granite, and then dealloy the ZNO from granite, introducing more porosity to that samples. It's important to highlight here that we are going to use carbon coke bed to produce the reducing atmosphere. But if we want to go in a greener way, hydrogen or even ammonia could be used as this oxidizer of these reducing agents. Okay. But our idea, as I have already mentioned, is we have a chemolar mixture of aluminum and zinc oxide. They react, form the porosity we have already seen, but at low content. And then we apply the dealloying process, making the zinc volatilizing from this structure, and then increasing the amount of pores. For that, we use coke bed firing for 5 hours. We saw by FactSage that the target temperature was 1100, but because FactSage neglected kinetical effects, we also tested 1200 and 1300 degrees C. And here we track the mass loss and the amount of zinc measured by fluorescence. And we can see that in fact 1100 for 5 hours were not enough to generate too much zinc loss and neither mass loss. Okay? But after 1300, we saw almost plain granite, almost plain column at the sample because all the zinc oxide had volatilized. And now I have just aluminum in my sample. It's interesting to notice that this zinc that volatilizes due to the carbon coke, they deposit next to the boards of the crucible. So the idea, and this is pure zinc oxide, make some XRD here. And the idea is, if you want to implement this commercially, you can have a closed cycle in which we can take this zinc oxide and grind it and reuse with alumina to produce granite and so on. Okay, so we saw the mass loss, but let us see also the volume of pores, the porosity. And in fact, as I have the volatilization of zinc oxide, I have the increase in porosity, and I can reach up to 60%, of course, which were our initial target to compare the microstructure with the 60% of core alumina porous alumina produced by sacrificial template method. And this makes sense because alumina with zinc, and I react alumina with zinc, I produce 30% of porosity. And when I get rid of this zinc, I get another 30% of porosity. So now I have material with higher porosity. The question you are going to make is, well, but how was the pore size after this process? Did you change it? It's bigger, it's smaller. So let us see the dealloy. Now we call it dealloy sample for 13 degrees there, 13,000 degrees C, 300 degrees C for 5 hours. We have almost the same microstructure now with higher porosity, and the pore size was also narrow and close to 0.7 micrometer within the ideal range here, but now with much higher amount of these pores. Okay, but now we're going to say, well, but will this pore remain stable at high temperatures? Because you are talking about thermoinsulators, you need higher temp to be applied at higher temperatures. It cannot be so sensitive to temperature that the pores will shrink and during to sintering disappear. And we took these samples, applied another thermal treatment now at open atmosphere, 1500 degrees C for 5 hours, and we saw small changes in the microstructure. So we retain the porosity and we are still in the ideal pore size. Very nice, but I'm talking about thermoconductivity. If I stop the presentation here, it will be strange because you have been able to produce the type of microstructure you want, but what about the property, thermoconductivity? And then the last slide, last characterization I would like to show is the thermoconductivity of 1200 degrees C. Here, for the different materials, we can see that as expected, the dense alumina has a much higher thermoconductivity, right? KF. For the AC, the alumina, the pores produced just by Kirkendall effect, so the ideal size was ensured, but with lower porosity, we have almost the same behavior as the sacrificial template one. If we take a look closer to this region, we are going to see like this. So these both alumina, the sacrificial template one with higher porosity but higher pore size, have almost the same thermoconductivity than the sample AC. And when we introduce even more pores by the DL1 process, now we have a much lower thermoconductivity, proving our point, our calculations, that not just the porosity is important, but also the pore size is important, and we need to ensure that we are in that range of 0.5 and 3 micrometers. So just a brief slide and conclusions. We said we need better thermal insulators to enhance the efficiency of our process, and then inhibiting providing less carbon emission. For that, we need to obtain pores within the ideal size range. And in situ reaction could be a good strategy to obtain such a pores, such microstructures. We saw that the Kirkendall effect in the formation of granite results in pores that are quite similar to the zinc oxide particle size. In these systems, the porosity is limited to 36% volume percent, because this is the amount of ZNO in the plain granite formation. But we can use dealloying-like process to get rid of the zinc and obtain an even higher material with even higher porosity and keeping the ideal pore size range. And with this, we have proven a lower thermoconductivity. So, although further tests are required, we need to understand the system, how it works, how it performs with under exposure at high temperature for longer times, and so on. Using in situ reactions is a promising approach to design advanced ceramic microstructure. Here we were talking about thermoconductivity insulators, but not just thermoinsulators. We can think about other possibilities of using this in situ reaction to have advanced ceramic microstructure. With that said, I would like to thank you all, and I'm open to questions. I forgot to take the time, so maybe I have pass some minutes.
Thank you very much, Otávio, for the presentation. It was 30 minutes, and we have time still for a question. Alexander,
Thanks for your great presentations. Can you please go to slide 19?
19.
So yes, so here we have your thermal conductivity of the specimens. What's the values of the isolators used in the industry at the moment?
These type of insulator or in general.
For typical isolators used in the industry in general, yes.
Yes, usually we have some insulating layers in almost all equipment. So in steel ladle or iron-type degasters, it's common to have insulating layer to prevent thermal losses, increase the efficiency, and so on. But these insulating layers usually are made out of fibers, ceramic fibers, aluminum, silicoaluminate fibers, which do have a low conductivity at lower temperatures, but not at higher temperatures, because the microstructure is not optimized to interact with the radiation. So this is one point. It's not so effective. It's the fiber insulators, so it's not so effective, but it's cheap, but it's toxic. The fibers, especially during installation, during production, these fibers can aspirate in the air, and if you intake it, it will go straight to your lungs and cause some problems. So industries that use this type of materials always have implemented some rules trying to get rid of fibers. Especially in Europe, they are really trying to get rid of fibers, even though it will lead to a higher cost of product. So even though it has a higher cost, we expected that the eco-friendliness and the performance will pay the price. Thank you.
Another aspect that they tell us that although we measure to 1200 centigrade, you'll see the trending that it's going down. That means the radiation has been blocking. And the point is at 1500 centigrade, because we have a refractory, we expect that the thermal it's going to be at the level of thermal insulation without the problem of toxicity, shrinkage, densification, then we believe that is progress.
First, we would be very interested to measure higher temperatures. Our technique here, we use laser flash analysis. It could only reach 1200, but of course, reaching 1600 will be very promising, very interesting to have this type of results to see this trend here. And this one, because it's a sacrifice, bigger pores, it tends to increase as it happens in fibers, while the ideal pore size range should lead to a lower, even lower thermal opportunity.
Thank you very much, Otávio, for the presentation. Thank you, Alexander, for the lecture. Going to Alexander. It's a consideration. So I have for the thermomechanical characterization of conventional magnesium thermal structure grades with and without magnesium thermal recycling. I would like to tell the presenters if you have some conflict, just go outside, start yourself. Alexander, please.
So first of all, thanks a lot for being here. It's a pleasure. It's an honor to be here. We have a lot of fun. Yes, so I'm one of the lucky PhD students of the research training group. And Patrick already told you something about the two core ideas. So we have one core idea dealing with the upcycling, and I'm belonging to the group dealing with the recycling. And in my opinion, one of the things that makes our work especially exciting is the collaboration between Borges and steel, so the industry. So, but now let's talk about the motivation of the recycling group, of the research training group, and my presentation today. So, according to this source, approximately 28 million tons of refractories are consumed every year. However, the estimated share of refractories used as recyclate for the production of new refractories is below 10% worldwide. As you know, the MgO-C, the carbon-bonded magnesium refractories have established themselves as linings for the converters or for the electric arc furnaces, but also for the ladles. So this picture here, you can see a ladle during the removal of spent MgO-C bricks. And if we are producing 1 ton of crude steel, the consumption of the MgO-C is up to 4.6 kilogram MgO-C per ton. So on a global scale, considering the worldwide steel production, approximately 1.8 million tons of steel every year, that's up to around 8 million tons of spent MgO-C. So this is a resource we cannot or we should not afford to waste. The suitability of incorporating certain amount of recyclates has already been proven in the literature. And what's more important, commercial MgO-C refractory bricks containing these recyclates are already available. So, but it's also important to consider that the incorporation of these recyclates affects the performance of the bricks, and which is what we are investigating in the recycling group. And I'm particularly interested in the thermo-mechanical properties of the bricks. So we received 3 commercial MgO-C bricks manufactured by Refractories steel. So one brick, you can call it material F, contain only fresh raw materials with 98% of fused magnesia and 68% of plate graphite. And in the microstructure here, you can see SAF mesh and BSE contrast. And you can see that the microstructure clearly contains porous MgO aggregates, shown in the light contrast, and the maximum aggregate size is up to 7 millimeters. And then we had the 2 other MgO-C bricks, material R1 and R2, where 50% of infused magnesia was replaced with the recyclates. So here, in this microstructure of material R1, you can clearly see one single recyclate, and it has a higher porosity. It is already partly cracked. You can see it by the black contrast, and therefore redamaged. And if we are introducing recyclates into the MgO-C refractory bricks, we are also introducing the sintered magnesia. And the sintered magnesia, as you know, has a higher density compared to the fused. And yeah, you can see the both microstructural images, but we are also introducing this type of magnesia. But in general, also important to consider that we process of the recyclates vary batch to batch due to their different origins and inherent heterogeneity. So the recyclates used for R1 and R2 differ mainly in their carbon contents. And these carbon contents roughly covered the full range found inside recyclates, and also, of course, directly affected the total carbon contents of the bricks. So we had the total carbon contents of the bricks of 12.4 weight% for material R1, 8.7 weight% carbon for R2, compared to 11 weight% for material F. And all the bricks are, because of the recyclates containing already the carbon, only 5 weight% of freshly added flake graphite was added to the materials with recyclates. And all the bricks were produced under industrial conditions, so using the big pressing devices and using also the same phenolic resin liner, and no antioxidants are used. And it is also important to consider that the incorporation for recyclates led to a decrease in the bite density by an increase of porosity. And these properties were obtained after cooking at 1000 degrees Celsius. So, move on. Fast. So we received these commercial bricks from the company, and we are used wet cutting and wet drilling with diamond tools to produce our desired specimen geometries. And if this specimen, so with the cylindrical specimens, you can perform compression tests, of course, and for the bending tests, we use such specimen bars. And it's also important to consider that all the specimens were cooked at 1000 degrees Celsius at 3 hours boiling time. And finally, we have the thermo-mechanical high-temperature testing device, which you can see on the picture. And it has an integrated protective gas chamber, which you can see here. So we can carry out our tests at temperatures of up to, let's say, 1500 degrees Celsius, using, for example, argon atmosphere. And in my case, I just performed the tests with the grades, for MgO-C free grades up to 1300 degrees Celsius. So someone can ask why not higher, because the application temperature is, of course, maybe 16,000, 1,600 or even higher. So the reason for this belongs to the carbothermal reduction the magnesia, so the MgO-C reacts with the carbon, so with the graphite flakes, especially with aqueous carbon, and this leads to the vaporization of the magnesium vapor and also to the deposition of secondary MgO layer. And in our case, we are measuring the temperature with a pyrometer, so it depends on a certain emission coefficient. And if we get these deposition of flakes on the surface, so the emission coefficient change, and we cannot guarantee the correct test temperature. So it's limited with these devices and this sample type to 39 degrees Celsius. And yeah, as I should have mentioned earlier that we are using induction heating. So we have the water-cooled copper coil and the frequency generator. And this is a view inside of the protected gas chamber. And we can apply a compression setup, as you can see here, but also a four-point bending setup. So we apply a certain preload to the specimen, a range of a few Newton. And when we are heating with the induction heating up to the desired specimen temperature, target temperature, with heating rate of 5 to 10 kelvins per second. And where we have also take care of the temperature holding time to guarantee that the temperature is homogeneously distributed and we really reach the desired temperature. Okay. Yes. So this slide summarizes the experimental approach. So we received our commercial bricks and then we processed our specimen geometries. And we can perform compression tests and stress normalization tests, but also for bending tests and fracture mechanical investigations. For the compression test, the load was applied parallel to the former pressing direction, and in bending mode it was perpendicular to the pressing direction. And also additional microstructural investigations by using SEM and digital image correlation are carried out. And on the next slides, I would like to show you some of the results. But first, maybe we have a closer look at the MgO-C Crecyclates, which are, of course, obtained after the processing of the spent bricks. So this is an example of the fraction 1 to 3 millimeter. And here we use the SEM and PDC contrast to have a rough idea of what the composition of these recyclates is about. And you can see that the microstructure is, of course, differs from recyclate to recyclate, and it's in general very heterogeneous. So it consists of the MgO aggregates, which are shown in the light contrast, and it also consists of the carbonaceous matrix, which consists of the flake part, of the MgO fines, and also of the carbon residues remaining after cooking from the fiber. And the white contrast we also have is caused by the impurities, typically calcium containing silicates. So if you have a closer look at higher magnification by using the SE contrast, we can see that the surface is highly rough and highly jagged, and you can also get an idea of it. And you can also see lots of cracks in these recyclates, especially along the interfaces between the aggregates and the matrix. So now, how does the incorporation of these recyclates affect the general properties of the commercial bricks? So as already mentioned, if you are introducing the recyclates, this leads to an increase in porosity and a decrease in the bulk density. And the incorporation of the recyclates also led to a smaller average MgO size, as evidenced here by the computed tomography images comparing material F with material R1. When we use the X-ray fluorescence spectroscopy, we can also have some information about purity contents, and we could find that the recyclates also increases the purity content, but decreasing the light silica ratio, which you can see here, which is not so good. It also decreases the dynamic Young's modulus and decreases the oxidation resistance, but it increases the cold crushing strength. This is the surprising finding. The reasons belonging to this I would like to address later points in this presentation. But now let's talk about the results of the thermomechanical tests. So we carried out the 4-point bending tests, and we determined the bending strength values under these test parameters of the 3 MgO-C brick rates, and the temperature range from temperature up to 1300 degrees Celsius. And you can see that the lower total carbon content was correlated with a higher compressive, with a higher bending strength values. So in the case of material R1 containing the lowest total carbon content, we could find out the highest bending strength values. So in this context, no detrimental effects of a recyclate on the bending strength was found. For the 4-point bending test carried out at room temperature, it's possible to remove the induction coil. And then we were able to use digital image correlation in this context. And by using a digital image correlation, we are capturing images at certain intervals along the bending stress total deflection curve. And the images were used to identify the strain localization and also the particular cracks. And we are displaying them as a false color images. And for the material under increasing load, which you will see in the video starting soon, the material F showed this behavior you can see here, hopefully. You can see that the sprays, but also cracks, may occur at the interfaces of the larger MgO aggregates and the surrounding matrix, and they occur at the bottom side, specimen R, which is logical because it has exposed to the highest anti-stress. And the material R1, which is going on now, also shows a similar behavior with a strain localization occurring at the interfaces. So the crack formation and propagation already began in a distributed manner, though not just localized along position. It began in a distributed manner even before reaching the maximum bending stress value. And this resulting in an unelastic or nonlinear material behavior is also evidenced or indicated by the curvature. So it's not a straight line like in a normal linear elastic material behavior, it's a curvature. If we are increasing the load up to the maximum bending stress, you can see the crack propagation occurs with both materials. And beyond the maximum bending stress values, you can see that lots of things going on. We can call these things energy dissipating mechanisms, leading to increased fracture toughness, and also correlated with the improved thermomechanical or thermoshock behavior. For example, we have the formation of crack networks, we have crack deflection, and we have crack closure, crack bridging, crack branching, and also, of course, frictional effects, dissipating energy from cracking. Okay. And after the tests, we can also have a look at the main crack paths, and we can classify the cracks into 3 different types. So we can see it here in the case of material closer look in the specimen surface, and you can classify the 3 types. We have cracks along the interfaces of the MgO aggregates into the carbonaceous matrix. We have also cracks within the matrix, and we have cracks within the MgO aggregates. And you can clearly see that the highest proportion of the cracks occurring along the interfaces in the case of material F. And if you have also look at the material R1, recyclates, it's a similar behavior. We have small differences. In the case of material R1, we have a smaller fraction of cracks within the MgO aggregates, because in this case, has a smaller average MgO aggregate size. The bigger the MgO aggregates, the higher the probability to have a critical defect. And we also have a little bit of a increased proportion of the interface cracks, but in general, that's a comparable behavior. So in the scope of the compression test, we determined the compressive strength values of the three grades again, and also in the temperature range from room temperature up to 1300 degrees Celsius. Here you can see a specimen of material F after the compression test again at 1000 degrees Celsius. And you can see that the protective gas chamber works, so you know significant oxidation to observe here. And you can see that the recyclate containing grades are 1 and are 2 show the highest compressive strength values across the entire temperature range. And furthermore, the material F, which is shown in black, you can see a decrease in the strength occurring at 1200 degrees Celsius. So in the case of R1, the decrease occurs at 1300 degrees Celsius, indicating improved thermomechanical stability. In the case of R2, unfortunately, we only could obtain the compressive strength values at 1300 degrees Celsius due to the load limit on the testing machine. So in this case, it would be necessary to reduce the diameter of the specimens, and we don't want this because the MgO aggregates are 7 millimeters, and it's already a little bit critical with these diameters around 20. So we need always lots of tests for the scattering of the properties. Okay. And now let's have a look at the green tests conducted at 1200 degrees Celsius under a constant force of approximately 6,000 Newton. And they were performed for 6 hours, and you can see the green strains over time. And also here, both recyclate containing materials have smaller strains, grip strains, and therefore enhanced grip resistance compared to the material F, so compared to the conventional. Also, if you have a look at another experimental setup at another institute, so completely different conditions, and we performed some refractoriness under load tests here. And refractoriness under loads means that we have cylindrical specimens which have a higher or larger dimension, and they were heated with a specific heating rate of 5 Kelvin per minute to the desired target temperature of 1600 degrees Celsius, and we are measured the change in specimen height. And as expected, all the MgO-C brick rates showed a thermal induced expansion, increasing temperature, which is clear. But the lower total carbon content lead to a higher expansion, let's say. In the case of R1, which has the lowest total carbon content, we have the highest elongation. And this is because MgO has the higher thermal expansion coefficient compared to graphite or amorphous carbon. And you can also see the improved thermomechanical behavior of the materials containing recyclates here. Because we applied load of 0.2 megapascal, they led to a decrease of they lead to a compression of the specimen at 1555 degrees Celsius, but both recyclate containing materials showed no compression up to 1600 degrees Celsius. So even if we have higher temperatures exceeding the 1300 degrees Celsius, now maybe also in this range the behavior of the low melting impurity phases, which are dependent on the lime to silica ratio, came into play. And even here, under these circumstances, although the total carbon content is very different, both recyclate containing materials show better behavior. So, summarizing the results, no detrimental effects was found in the range of the, or in the context of the bending strength tests. Under compression tests, we could even observe the improved mechanical behavior. So the big question, of course, is why this happens? And now maybe let's have a look at the microstructure of material R1 containing the recyclates. And we can see one, I would say, estimated recyclates in the microstructure, which is outlined by the white dashed lines. It's always not so easy to say if this part belongs to recyclate or not, because they are usually very good embedded in the surrounding microstructure. Here, I determined this estimation, or it was estimated because of the incorporation of the sintered magnesia. So this made me, it was kind of a clue, but it's maybe it's a recyclate. And I also made this estimation, let's say, because of the orientation of the graphite flakes, which also aligns along the recyclates very impressive feature. And yeah, if you have here a look at the interfacial area of the recyclate here upper end and the surrounding carbonaceous matrix of the microstructure of material R, we can see that pronounced interlocking occurred, which results in stronger mechanical adhesion. And it is also possible that even chemical bonds maybe could form with or between the carbon atoms of the bind and between the carbon atoms of the carbonaceous matrix of the recyclates, which also, of course, would improve the adhesion. And in general, the adhesion of the MgO-C recyclates relies on mechanical interlocking. So there is no chemical reaction between the MgO and the graphite, carbon, and the surrounding surface. Relies on the mechanical interlocking. And as I already said, in this context, the recyclates has a higher roughness, increased the porosity. So this leads to an increase in the surface area and also improves the adhesion. So other reasons for the improved mechanical behavior under compression were attributed to a reduced fraction of freshly-added flake graphite. The flake graphite can do some things like crumbling and sliding, and also contributing to deformation at high temperatures. And if you have a reduced fraction, this can also affect the thermomechanical behavior, of course, and also the differences in the MgO aggregate size could also be part. And on the other side, we have to consider that recyclates have lots of defects. And these defects, of course, are not critical in compression because they are compressed. But under tension, they are way more critical, which matters, of course, in the bending tests. So in this context, this may explain why positive effects under compression are reduced in the bending mode, and making this, in our investigations, the total carbon content with this decisive factor compared to the recyclates. I would like to discuss this further with you, and thank you a lot for your attention. Also, of course, thank the DFG for founding the project, and I'm open to questions.
We have again time just for one question. It's better to ask, otherwise I ask again. Thank you for the very nice presentation. You mentioned at some point that the impurities from this recycling material can induce liquid phase and use on under refractories under load. Have you tried to calculate the using FactSage, for example, the melting point of these impurities and how they will interact with other phases? Is something that you think is possible?
So we know about the melting points of the common or typical chromatic impurity phases, which we also found by using X-ray diffraction. So we know what phases are present, but we did not simulate by using the actual compositions. Yeah.
But do you think this is an important thing for the mechanical behavior as a whole, or it's just minor impurities and it will not play a significant role in the material? Good.
It certainly has an effect, especially on the creep properties, but in the results, especially in context with the refractory and results, no negative impact was found. But in theory, it has negative effects. Thank you.
Just actually quite. You didn't mention anything about the effect of antioxidants because in the recycled material, perhaps they have used aluminum silicone as a antioxidant. And you know that it improves the mechanical properties at high temperature. Couldn't be also the effect of some antioxidants in the recyclates that could be improving your mechanical properties?
Excellent question. Then we have a look at the X-ray fluorescence results showing the alumina contents, for example, for both grades. And you can see that there is not so much of a difference in the contents of the typically used antioxidants. And also, sorry. So yeah, so it's not that significant in the case of alumina or maybe also silica. And also in the case of the scope of the X-ray diffraction, we could not find. I had a look at, for example, alumina carbides or other phases like spinels. And by using EBSD, I could detect spinel phases inside the recyclates. That's true, but very small proportion. So it, of course, can have an impact. I won't say that it does not have any impact, but it's very reduced in my opinion. But it can contribute.
Thank you.
Thank you.
Thank you again, Alexander. Now, the next presentation is going to be Dr. Falsetti, that is going to present a framework for predicting slag objects and investigate an alternative involving conditioner in the fire furnace. Thank you.
Just waiting for the presentation to come. Just together. Just turn on the later one. This control panel. Yeah, try. Okay, so thank you everyone for being here. It's been a pleasure. I guess in these own very different aspects. So socially, personally, definitely it's been a pleasure to interact with you. We'll have you also been here, the University of Carlos. Today, I'd like to talk about slag foam and also how it can predict the properties of the slag based on its composition. And we know the importance comes from the transition that you're having today from production of steel based on the blast furnace and also based on carbon from a route that you're basing the composition or the basis of the production of steel is based on hydrogen. So that basis the purchase of carbon to hydrogen. And also the middle here, you know the importance of recycling of the steel also to reduce the carbon footprint on the production of steel from the steel industry. So what's common between the recycling of steel and also the production of steel by use of hydrogen is that we rely on the electric arc furnace. So this is one of the reactors that we have in steel making is becoming more and more important Although we do have some differences when we talk about the electric arc furnace from the recycling or from the electrical route to the hydrogen route. But basically, something that can happen inside this furnace is the foam of the slag. And Otávio was talking about the importance of thermal conductivity. We know that when you remove the foam of something, you insulate this thermally from the environment. We know that from the glasses of beers that you can have. So we know how it insulates like the heat from the exterior to come to the liquid. But in this case, our liquid is the heating source, so we're just insulating this from the environment. And also, as Patrick said about the consumption of electrons, it also obstructs the electric arc furnace. So if you want to minimize this consumption of electrons here, it can also insulate them from the environment and also reduce the radiation that goes from the electrode to the other parts of the electric arc furnace. So talking about the foaming of the slag, the foaming of the slag is pretty much the same as the foaming of an aqua solution of suspension, for example. And you do have some mechanisms that act to collapse this foam. So, namely, we can talk about the coarsening of the bubble. So, as we have different sizes of bubbles here, each bubble has its own Laplace pressure. And by this difference of pressure, you can expect some diffusion of gas from the smaller bubbles to the large ones, leading to the coarsening of this bubble. Also, bubbles are composed by air, but they have some fluid in between them. As this fluid goes by gravity to the bottom of the funnel, we have what's called drainage. So here is one bubble separate apart from another one. But as we drain this liquid here, then this film becomes thinner and thinner until it eventually breaks. And when it breaks, we have the qualities between bubbles, just like two bubbles become one. And if this qualities happens to the atmosphere, we call this a rupture of the bubble. So I have this collapse of the foam. The interesting part is that we can model each of these mechanisms by some equations, and these equations are based on three main parameters. So the surface tension of the liquid with the gas, the viscosity of the liquid, and also the density of the liquid. And this is also true here. So the point comes, if we know the properties of these slags, can we actually model what will be the behavior of this foam if you are going through a good direction, if you are spoiling the foam of this. And talking about chemical composition, we know that we have base compositions for slags, but you can also think about different conditioners. And in this conditioner, I would like also to try here the recycled raw materials because yes, as Alexander said, we produce millions of tons of recycled spent refractories each year, and we are looking for ways to recycle them. Some of them, like in the premium part, can be used for refractories, but the not so premium part, maybe you can try to use that as a slag conditioner, so changing the composition of the slag. And in the electric arc furnace, we have some additional benefits that I would like to discuss by the end of this presentation. So basically, our main goal here is can you estimate what would be the foam of the slag based on its composition or how it changes as we condition the slag with these alternative conditioners? To do that, we can do that in many ways. We can have models to, for example, assess the viscosity of the slag. We have models to the surface tension and to density, but they're not that reliable. But something that we wanted to explore today is we do have a really large database here for glasses and melts. And of course, glasses and melts are not that close to slags because their chemical composition is different, but the fundamentals relying on them, on the liquid and the structure, are basically the same. So we can use this base of glasses to have a machine learning model trained, and this you can get from the literature. They did that for glassnets. So from these over 200,000 compositions of glasses and melts, they took 10% for the validation of the model, trained it with 90%, got really nice results, really nice confiability, reliability on this model.
And by applying this artificial neural network algorithm, they can estimate the properties of surface tension, viscosity, density, and over 25 properties more related to glasses, of course. But in this case, our question is, can we use a pre-trained machine learning model based on this huge database of glasses and melts to apply to slag properties and then apply them to estimate the foamability? Of course, we have to validate this model first for slags. And how we do that, we compare with experimental results from the literature, and for that, we have a Bible of slags, which is the slag atlas. From there, we can get hundreds of figures for these properties and also some dozens of tables. So the work here was to extract them, and by extract, I mean analyzing these images and get like each point of composition, getting the value for these properties, putting that on a table, and then we added up with some properties for the system that you're interested in. So filtering that compositions of the base slags and the conditioners. So here I have over 500 viscosities, 200 surface stations, and 90 densities to compare the reliability of this model. Also, we know that there are some commercial solutions to estimate the viscosity, and in this case, to calculate the viscosity. They are based on the structure of the slag. So, as I said, the structure of the slag is pretty close to glasses. So, we have this silicon oxygen network here. Then, depending on the atom that you have in solution, you can have 4 bonds, you can have 3 bonds, so bonding and non-bonding oxygens in the structure. And based on this on the composition of the slag, you can predict by computational thermodynamics what should be these different pairs here of silicon to silicon or silicon to calcium, and etc. And by doing that, just for the temperature. And by the end of the calculation, we have the viscosity as a function of the composition and the temperature. So this was just a benchmark for us, just to know if the model was good enough, like the glass knife was good enough to predict the viscosity. Unfortunately, I don't have other models to compare for density and surface tension, but luckily those were the best results that we got for the other properties. So just checking for the reliability of the model. First of all, when compared the viscosity of the experimental values, so coming from slag atlas, the predicted values, I know this is not so good. There are some reasons for that, because the database was made for glasses. So typically you have higher contents of silicon, higher contents of silicon had higher viscosities. So that's why when you check here for the R squared, it's 0.17 or close to 0.18, really low level. And compared to FactSage, we are talking about 0.97. So for those who use FactSage, continue doing that, you're doing a great job. And so for the viscosity, I would say that cannot rely on less than. Of course, if you don't have a FactSage at home, you can use this for a first guess, but I don't trust that so much. So for the second property, we can go for surface tension. We are increasing here the R-squared value. Of course, not the ideal. We're talking about 0.68 for our system, but we start to have some kind of correlation between the results, the experimental and the predicted ones. There is a drawback here on the glass that I have to use, because although for viscosity it predicts like a continuous range of temperatures, for the surface tension and the density is only for discrete values of temperature. So the highest that you can go here is 1400. It's not that much, but even though we can get like from the effect of the chemical composition, what will be the effect on these properties, not taking so much into account for the temperature. And that's why we see here these alignment points, because although experimentally you are changing the temperature of the system by keeping the same composition, for glass knife it's pretty much the same system, because you're always accounting for the same temperatures. Just one disadvantage of the model. For this, this also happens. So if you check here for the highest temperature, that's the lowest correlation. But in general, when you consider these points, you're talking about something close to 0.81, and using a model that was pre-trained on a really large database. So, but I'm not here to talk just about the properties of slag, when to use them for something, right? So when you go to slag foaming, as I said, we have these equations, and let's take it the best of the two worlds. So first of all, we run some calculations on fluxation. We extract the solid fraction of this slag, also the composition of the liquid, and with the composition of the liquid, we can calculate here the viscosity. Of course, cannot use this for phosphorus and chromium because they are not on the database of fluxation for the viscosity. But we can couple these results with some predictions of glass density, thinking about surface tension and density, and then apply that to these equations of the foam. Just to have an example here, we consider common vertical composition of this slag inside the electric arc furnace. So we're talking about a binary basicity here of 1.5. We started here with a really high, but a high content of MgO because the author said that this would be the content to keep the slag saturated throughout the process. But you know that this is not so true in the industry. Sometimes they work with not so saturated slag here, so it can become liquid during the process. And we assume that the FGO will vary within this range, so from the onset of the process to the refining of the steel. And we're going to check if sodium will be an alternative conditioner to this system because we have two effects of sodium. The first one is that it reduces the viscosity. So from one side, it's not so good to the formability, but from the other side, it's a surface active compound, meaning that we lower the surface tension, and by lowering the surface tension, we reduce the Laplace pressure between the bubbles, the difference of the Laplace pressure. So by doing that, we have results like this. I'm not spending so much time here on the density because you see that it doesn't account so much for the difference in this in the equations for the time scales. But if you check here for the surface tension and for the density, we can see what we're expecting to see in the for the effect of sodium. So just having here the amounts of 0.5 and 5. This is like 1 order of magnitude higher, one from each other. Because if you have just 0.5 here of sodium, we decrease the surface tension, but we don't decrease so much here the viscosity of this layer. Because if you add 5%, you go from this point to this point, meaning that you really decrease here the surface, the viscosity, and you don't drop so much the surface tension. So yes, sodium is a surface active compound. We can reduce the surface tension, but still controlling what will be the viscosity of the system. And something that I want to point out here also, if you compare the influence of sodium to the influence of the grease in the iron content here, sodium doesn't play so much of an effect when compared to the increase of iron that will happen throughout the process. So of course we have to take care about the amount of sodium when we talk about the onset of the foaming. So to start the foaming on your process, you have to be careful about sodium, but once that you have some foaming on your process, maybe you can add some sodium to keep this slag lasting for. Those are the properties that we're going to apply back on these questions. It's something that I really have to mention is that these questions they are based on the time for a bubble to rupture or a mechanism to happen. So if you increase this time, it means that the bubble is lasting more time. If you decrease this time, it means that the bubble is lasting shorter. And in this case, what you can see is that, well, as expected, the process of generating iron here reduces these times. So as we go further on the foaming of this slag, actually on the refining of this tube, it gets harder and harder to promote the foaming of the slag or even to keep it. But when you account here for the influence of sodium on the coursing mechanism, you can see that sodium increases, and here see again the importance of 0.5%. It's not that much of sodium, but you increase here by 10% this mechanism, and it keeps throughout the process. So iron here doesn't have so much of an influence on this mechanism. On the other two, although sodium and basically the viscosity, the dropping viscosity caused by sodium drops also this time for the mechanisms to happen. The drop caused by iron is more significant, so this drop will happen anyway during the process of the exchange. So just going with the slide, summarizing the points that I was saying, we can see this effect of sodium in the different aspects of the forming of the slide. So moving to the conclusions, but before the conclusions, I need to have an outlook to the recycling of refractory materials, so stage refractories. We saw that you can use this coupled framework, so merging fixation with glass lens to obtain the whole properties of the slag and apply this to estimate the performance of the slag. Talking about sodium itself, we saw that 0.5 would be a nice initial target for the process. So we have some effects on the viscosity, but the main effects are not on the surface tension. And now the outlook, it opens an avenue to test alternative compositions. We do have some cases that, for example, people want to remove fluoride from fluoride from the process. So moving from fluoride to water alternative condition can be we can use this framework to study. And also when you think about the use of recycled materials inside the electric furnace, we know that every time we're trying to condition this slag to have the proper amount of MgO, really we do this by using some virgin raw materials like lime or dolomite, but you can also use here some recycled raw materials like MgO-carbon refractories or even dolomite fines from the process. And there is a nice advantage here because in this case, you don't have to remove the carbon because we need to input carbon in the electric furnace, so we can reduce the consumption of carbon by using these special refractories to condition the slag. So, what would be the influence of these spent materials on the properties of the slags? Because, as Alexander showed, sometimes you have really nice raw materials with no contaminations, but sometimes you can also have some raw materials with, let's say, chromium, manganese, or phosphorus contamination. So how do you deal with that? How do you predict what will be the influence of these contaminations? Then you can apply this framework and check for the properties of these slags. Here I just mentioned one of the properties, one of the, let's say, the processes that can use slags promote the foam inside the electric furnace, but this framework would also be applied to, for example, estimate the discretization or the performance of the discretization, the slag affirmation, the inclusion removal, so anything related to the properties of slag can trace back to this framework and then predict the viscosity. So as I said, it's been a pleasure to meet you. So I'm looking forward for some discussion, some questions, and thank you so much for being here.
Very much. So, sorry. Well, I cannot ask it.
Yes.
From myself, I'm not so familiar with the electric arc furnace process. Do you have possibility to add slag conditioners during the process? So
So we have this spending of the electric furnace. So it would be better to start process with the right of this, like rather than like adding different injections. Although in some points, because just to promote the fault of this, like of course here was like a summarized process. But if we think about these different reactions that happen inside the electric furnace to generate these seal bubbles, I'm almost there. Yeah. Look is the first slide. Yeah, no, that's no. There. Okay. So when you see like an account for these reactions, for example, you see that oxygen is reacting with iron in the molten phase, but also you have like the the iron oxide generated here reacted with carbon, or even like the carbon reacting with the injection of oxygen. So they do have some injections during the processing of the steel inside the electric furnace. So then you could tailor the composition of these fines that are injected to condition this like first and more limited than the initial like the whole set of the process, but still can adjust something. Thanks for the question. It was a really nice one.
Thank you very much, Luis. Comments on slide and the title of the talk is Prospects of boron-freeself-glazes for coating of isostatic resilient aluminum and carbon functions. Thank you very much.
Before I start, I would also like to thank you all for your hospitality. You made us feel very, very well, and we have a very nice time, and we all really appreciate it, and we're really grateful for the efforts you made for our. Yes. First, boron-freeself-glazes from cold-isostatically pressed aluminum carbon functional refractory entitled over half a century ago, carbon bonded refractories were a breakthrough in the refractory industry. They reduced the refractory consumption dramatically, and since then, they're irreplaceable for all casting processes of metals. And if we go to the steel production, approximately 100,000 tons of isostatically pressed components, functional components. We're talking about monoblock stoppers. It's not working. Oh, we have to hold for a while. And then there's a can you do the laser point? Yes, okay. It's monoblock stoppers, some nozzle sledge shrouds, and also slide bay plates. We look every year. Here you can see some examples from some companies. You see the steel flows from the ladle through the ladle shroud to the tonnage, and from the tonnage to the molds. It's regulated by the monoblock stoppers, and you can see as a system with the submerged entry nozzles. And we have to say that it's a very critical point because it's the last step of the steel production. So any contamination or any reaction with the steel melt is not allowed. And especially if you see or if you think about boron compounds, these functional components have a base material, which is alumina carbon, so carbon bonded alumina refractories. They have a high carbon content, in particularly graphite. Laser shrouds have the highest amount of graphite. Monoblock stoppers and submerged entry nozzles somehow less. Of course, carbon is oxidizing at 400 degrees C for the binder system. It's the resins they're used as a binder. Graphite a bit higher from 600 degrees C, but of course application temperatures up to 1600 degrees C. So we cannot use them without protecting them from burning out. So we need a glaze application externally in order to protect them from oxidation. And we have specifications of these for these glazes. I haven't come to any composition of the glazing systems for functional components without boron compounds included. I don't know. I'm sorry for that. I don't know.
It's not moving forward, or
Doesn't make anything.
no?
Anyway, yes, the glazes have to have a very soft road softening interval, so they have to be working from 500 to 1400 degrees C. In ideal case, they have a slightly lower thermal expansion coefficient, so the components are under compression. Of course, they have to have a high addition to the substrate, and of course, no presence of any kind of defects like pimples, fissures, or strains that would allow oxygen to intrude the kernel of the component and proceed with the oxidation, which would be cause of failure, which is also one of the common reasons of these products to fail. The reason we can see here, of course, all these components are attacked by modern steels and slags. We have subject to extreme erosion, corrosion, thermal shock, and so it's obliged to take a preceding step. And in this is as an example, we can see the temperature of preheating around 12 or up to 1200 degrees C. And if we look closely, we have restrictions of the oxidation time. It should go more than 2 hours because even after 1 hour of after reaching the temperature, oxidation could start. And in practice, in many industries, they don't really follow the schedule they should, the heating program they should, and this can cause problems of the components. So Professor Aneziris had the idea, okay, glazes are not the ideal concept up to now. What if we could develop a system where you can form a self-glaze on the outer surface of the components, so a body glaze, no external glaze necessary. And indeed, we were able to develop a system where we had the use of additives, 8% silicon, 4 weight percent fused silica, and 2 weight percent amorphous borax, so sodium tetrachlorate. You can see that it's a glass-like structure. The white grains you see are the root grains underneath the glaze. On the right upper SEN picture, this is after thermal oxidation at 1150 degrees C, 10 hours. And it's on the layer, self-glazed layer, and beneath. So we see the typical composition. Of course, it's a corundum grain, and unfortunately, we see the detail here, like underneath it, and we see it from the composition that it's a sodium silicates. I know we were not able to identify boron on the system, but with XRF we were able to identify a very slight amount of boron. Yesterday we had the opportunity to see that If back then I had the acquaintance to send some samples, of course I would be able to have much better results for quantifying the composition of this self-glaze. And there you see on the right, on the left down picture, an optical image of the self-glaze foam, in this case at 1225 degrees C, again isothermal 10 hours, and you see that it's very uniform and dense, because then we said, okay, let's see how it's working. So we tried to compare it with systems which were glazed. Ag23, we only have alumina and graphite in the carbon bond, no antioxidants, nothing. Then we had a reference, we focused on monoblock stubble compositions. So a reference composition of a monoblock stubble, all of the compositions or all of the samples have 23% graphite. Then the system I just said with 4% silicon, silica, 2% sodium tetrachloride. And we see the carbons there. And the self-glaze system, the self-glaze formation was conducted after the cold samples, heated up at 30 degrees C, 1300 degrees C, in 1 hour, so fast heating, and after 5 hours holding at this temperature. And if you see, as you see, it had remarkable oxidation resistance. It was even better compared to the reference, the self-glazed. And in the case of the, because we made it also with the standard procedure, we also glazed it. And it was similar to the reference stopper. We made a step further. We found a foundry to try to test it. So we preheated it for a couple of minutes at 300, 400 degrees C. Then we immersed it in a steel bath for 5 minutes. And as we can see, it remained intact. No kinds of oxidation or severe reaction. Of course, the time was not so long, so it was a problem to find a foundry or somebody from the industry to test it for a longer time. And it's still a problem to find some industrial partners which would risk such kind of tests. In theory or in the beginning, they are positive, something new, something. But if you go to the, you have to test it. Nobody takes the responsibility. The problem is boron. As I said before, all glazes are boron containing. So this is a bit problematic because it's already started to be banned in the US. In Europe, it's also in the critical list of materials, and you have many kinds of health issues. And on top of that, no steeler wants to listen to boron. Very slight amounts are good for the steel, but after that, you start to have a very high deterioration of the properties of the steel. And if you consider that functional components, the last step, you don't have any possibility to make any changes. So it's very risky. On top of that, the system I just described were cooked this composition at 1400 degrees C. So high temperature. No refractory maker which implement this kind of treatment, especially nowadays, or I think in the future it won't change either. So we then thought, what if we could change, modify this composition and replace boron, the boron compound, with other oxide systems to eliminate boron, to leave boron out, and also trying to reduce the cooking temperature to, let's say, normal or accepted regions, like 1000 degrees C. We kept the heat treatment, which is simulating, let's say, the preheating step of the components at 700 degrees C. And Patrick made a great job. He started using Falsetti. Initially, started from this system with 4% silicon silicate sodium tetraborate. So he made the calculations. He saw which temperature you have the melt formation, which was 25 degrees C below 1200 degrees C. And he also saw the output, how much of slag in the factory, so glaze formation, was the maximum border, which was around 15%. And after conducting many investigations and many systems, we also made the design of a term to reduce the amount of theoretical compositions which we could investigate. So with the design of the term, we could reduce them. And the target value was, of course, the oxidation resistance for the cell transformation. But we also kept in mind that oxidation resistance is one point, but application is the other point, and we also had to see and check how the refractories under load is looking. Here you can see the batches which were most promising from the theoretical point of view, from the results of the fact stage. After some, let's say, we had Patrick had the first brown order sum of compositions, and we were reduced more and more. What you should see here is that the additives which were replacing the borax was wollastonate, sodium carbonate, and fused magnesia. And in every case, the oxides, these materials replaced the fine alumina used. So from the 28.7 of the initial content of the fused alumina, it was subtracted to obtain the same composition. And B1 to B4, you should keep an eye. It's with the highest, with the high amount of sodium carbonate, and B5 with low amount of sodium carbonate. And in the rest was changing the amount of the calcium silicate and the magnesium components. In all occasions, we used, based on the sum of solids, 10% of the system. We use noble lab systems in our institute only for the reason that they have a much longer storage life. Of course, in the industry, they don't use noble labs, they use salts. But for us, it's not an issue to do that. And we also use the pressing aid for the isostatic pressing. So we use the nylon mixture to make the mixing and the granulation. of the aggregates. Then we used wet back cold-isostatic press. You see there, it says 1000 bar. That was the initial stage, the typical, what every industrial iso press is doing, increasing of the pressure, holding time, and then slowly depressing. In the last slides, I will show you our isostatic press has the ability, with the use of a pulsator, to make some adjustment, or we can use the pulsator from up to 65 to 65 megapascal. So we made trials with 20, 40, and 65 megapascals amplitude. In both during increasing the pressure and also at Pmax. In every case, the max pressure is the pressure indicator. In cases of applying the amplitude at increasing the pressure, the number 20, 40, or 65 is in the beginning, and the maximum pressure then after. And in case of applying the amplitude on Pmax, it's 4 times replaced the whole repeated. And then going down. And in this case, we have first the high number, which is the Pmax, and then the amplitude applied. We had 2 kinds of forms we pressed. On the one side, cylinder rods as 3 shapes for the tests for oxidation resistance and shock tolerance under load. And on the later step, from the most promising positions, we also pressed some model monoblock stoppers in order to cut the samples for characterization of mechanical properties, physical properties, and so on. Curing program up to 180 degrees C, and after that, carbonization. So the pyrolysis process in cold bed, 1000 degrees C for 5 hours. Cutting the cylinders into bars, and then, as I said, porosity density, pore-size distribution, CMOR, 3-point bending test, HMOR of 1400 degrees C, refractories of the load. Also greater than that. Doesn't want? Okay. Here I'll show you the circuit plots for muscles optimization. You can see in all 3 diagrams the interactions of the components, and you can see that the sodium carbonate is very, very beneficial, higher contents for the oxidation resistance. MgO, on the other hand, is not so good. The same you see with the calcium silicate and the sodium carbonate, that both you can increase and you have a good result regarding the mass loss, which is the lowest. Also in the MgO and sodium carbonate combination. What was not so good was the combination between these 2 compared to the sodium carbonate. And practically we saw that the sodium carbonate and the silicate, calcium silicate, promotes the oxidation resistance, and on the other hand, MgO promotes the high properties, high temperature properties, the refractories. So it was difficult, or the challenge was to find a balance between the two. Here you see the batches. We have put also the components, so you see sodium 1.5, MgO2. You can see exactly the compositions. And ALB2 is the reference, so with 4% silicon, 4% silicon, 2% sodium carbonate, Borges. And as you see, the B1 was the most promising, it has the lowest mass loss, and for self-place formation, what's very important is this region here, that it flattens. The reference, as you see, unlike poked at 1400 degrees C, when poked at 1000 degrees C, it's not protecting at all. And we have also two other compositions, the B4 and the B2, which have also flattening. So they have the effective self-place formation, but at a much higher level than B1. The rest of the compositions were somewhere in between. B5 had also a lower or the second lowest mass loss, but you see that the rate, that the oxidation rate continues to go on increasing. So it wasn't a good example to further investigate. So we concentrated on the B1 composition, and here you can see some micrographs on the left side. It's on the bottom, it's the self-plate observation, and right on top, this area is here. And as the other occasion with the sodium containing, so the borax containing composition, you see some spheres. And the composition was silicon, calcium, sodium, magnesium, aluminum, and of course oxygen. Of course, we have also carbon grains everywhere. And you see also the spheres, which also implies or indicates another advantage of these systems, namely self-healing. We also tried, after the self-place formation, we cut the surface and we heat it again to see if it's still active. And for the second time, it also worked. So it's really promising under this aspect. Here again, you see the elemental analysis. For you, it's maybe too boring. You have many more possibilities. And the glaze layer was dense, uniform, 300 to 400 microns thickness. And we saw that with the PSD is now of space, and you see again the elements of the composition. We had also some small precipitations of magnesium aluminide spinel, which is also typical for this magnesium aluminide spinel starts at 1200 degrees C. So it's logical that at this temperature we have small precipitations. And again, you see the elemental analysis of the system. Do I do something wrong? Here you see the two batches. B2 wasn't so good with oxidation, but was better from the thermal from the factors of the load. The properties are normal, let's say. The only thing is that at the hot modulus of rupture should be improved because they were lower than 5 megapascal. It's just too high for internal. Shows up. Stuck? Seems like it's gonna mess. System. They had to read my speaker, so super much hard system. It's coming back. Don't you check it? But the other thing. Yeah, it's not even. Which was yours? I didn't use mine. Yes, it's oh yes, for the is it better? No, sure. Shouldn't. Okay. I can show now that I have the diagram with the both side distribution, where I wanted to show that maybe the pulsator didn't have any positive effect compared to the linear increase of the pressure. But on the other hand, it gave us a tool that we saw effects. We showed that we had a shift of both sizes depending on the applied amount of pressure, maximum pressure. Increasing the applied pressure, we had somehow higher pole sizes, and with increasing the holding time from 1 to 2 minutes, we had this side. Why does it move? It's a very yes, the oxidation resistance in this case of all applied modifications of the cold-isostatic press in 100 megapascal. So we see that the best performance was achieved after the linear increase. Here is what I wanted to show you, that we saw that the main difference for the better performance is that you have higher pole sizes, a small or a slight amount of higher pole sizes compared to the rest. Because on the other hand, you see that the different amplitudes lead to no particular advantages. Of course, as I said, on the other hand, you will say that you can tailor somehow the core structure by applying the different kind of amplitudes and pressures. One of the reasons is probably the graphite, because graphite is flexible, so it's easier to adjust, let's say, the system and have a stable, because we had previous studies with oxides where we saw that it has some effects. So these are the 3 best compositions or the 3 best programs of the CRP. And you see practically again that you have the higher amount of pores in the region, about 10 microns. So it was able to first develop a system which is self-glazing and at low working temperature. The problem was the high temperature properties. We saw that MgO promotes high temperature properties, but it's not so good for oxidation resistance. On the other side, sodium carbonate and calcium silicate improves oxidation resistance but lowers the hot properties. So we have to further investigate to find the right balance between hot properties and oxidation resistance. As I said, Falsetti didn't give any positive effects, but we saw effects, so we could use it later or for other occasions. And of course, we also saw that if we machine it or if we polish it a bit with sandpaper and we have smoother surfaces, we have also an improvement of the oxidation resistance because of the reduced roughness. Thank you very much for your attention, and of course, this work would not be able to be realized without the foundation and the support of the German Research Foundation. Thank you very much.
Thank you very much, Dr. Vasileios. For the comments that we had with the grid presentation, and we have one just for one question.
Can I ask one?
Yeah.
Just copy the presentations. So thank you for the presentation. It's really nice to see like these devices that they use for flow control. And as you said, it's like the goalkeeper of the metallic composition. So you have to be really careful about what you're adding to the metal or what you're withdrawing from the composition of the metal. You mentioned when it's really part of the representation, the oxidation of the submerged integral. Yes. So this oxidation is based on the oxygen that is on the composition of the steel or on the oxygen that is like in the inclusions inside the steel. So what's the fundamentals of this oxidation of the SN? Or it's more just like a carbon pickup from the
what I showed is the oxidation of the cold samples.
Yes, but like in the application, you also
The application, if you say if you take the stoppers, for example, the main thing is that it starts the preheating, which is at low temperature.
Okay.
After application, the first steel that goes, all glaze goes to the slag.
Okay.
But then it's not important the oxidation because below the slag, which is also insulating, you have the carbon bonded material where you don't have oxygen anyway.
Okay.
And this is an advantage of the normal systems with the external glaze because you have a poor or let's say malfunctional sometimes external glaze, but you have a strong interior substrate. On top of the slag, maybe right over the slag, you have maybe 1400 degrees C. But some centimeters or 10 centimeters more higher, it's even lower. It's straight, so there is no critical. So 300 degrees C are pretty much. And also, after refractories at the load, we had see that it has of course bubbles, but it's still stable for this kind of tests. Thanks so much. You're welcome.
Thank you very much again. Like now, we'll open the space for special guests that is online, and as Dr. Patrick is improving, and we can drop our welcome.
Yes, thank you very much, Victor. So we have the chance from the DFG of Tobias Standauer is also attending to our workshop. So I'm very happy and appreciate that he has so found time to take part as an attendee, and really grateful and thankful for the founding by the DFG, our research training group and also the workshop. So thank you very much, and I hope you enjoy the time.
What's his name again? Sorry.
Tobias Standard. He's not speaking right.
I can see him.
Not in the secret.
Can you check this? Like everyone needed this information.
Yes,
Marcus.
no. I guess it was.
And this only to do this.
Not sure. I believe the speech and something. All just going to can say it. Yes. We can go on. Let's consider what
Okay, then let us continue changing over here. So we're not having more problems. And the next talk is by Dr. Murilo Moreira, and the title is polymeric fiber crack and refractory castable on the whole of microcracking on the permeability and cement of casting. Thank you very much.
Thank you very much, Professor Falsetti, for the introduction. And thank you very much for the opportunity to present this work. I guess that it was interesting to see that from all the presentation until right now, we didn't saw a lot about castables. So I think it would be interesting to just present a little bit on those topics. Also, it's like the same presentation that I'm intending tonight here, but I guess it will be for a different kind of public. So with that said in mind, the basic question that we want to answer here is how polymeric fibers can work during the drying of castables as an additive to increase the permeability. We all do know that it works, but how do they work? That is the question. And basically, to just set up the problem, when you think about the removal of water from castables, it is one of the intrinsic issues when trying to work with hydraulic unshapable fabric castables. This is usually alternative to the shaped materials. And if we pick, for instance, the stilettos, we can see that there is a recent trend of increasing amount of castables used in this kind of application. The reasons for that are multiple, and it really depends on the different contexts. If you think about the Japanese market, you can see that they are already adopting stilettos based on castables ever since the 80s. On here on the east side of Moreira, we see a little bit of a difference
Here in Brazil, we see that it starts to get traction on this kind of trend and patterns. And some of the reasons for that would be related to the possibility of automation of installation of these kind of materials, a higher reduce of carbon dioxide emissions. Because if you compare the life cycle of a shaded product, usually would need to actually have a first heater and a fire before you set up the system, and then you preheat this whole system. When we talk about the monolithics, usually you can only have the initial preheating from the start and finish with an end product with the current shape and properties that you would need during operation. But there is a catch. As we said, the drying is the most important and longest process of application of this process. And the reason for that is that if we are not careful enough when removing the moisture from the material, that moisture can pressurize to levels of pressure that can lead to cracking and even explosion of the whole system. And this is not a problem that is only for our own community. We can see, for instance, that is a common issue when designing the launching pad of rockets. And to understand the mechanisms, we really needed to address the characteristics and the behavior of the castables, as seen as a multi-scale material, as we have different processes that go through behavior of water inside the micropores. And here we are talking about water that did not react with the binder, but also the water that is present in the hydrate phases. All of this water needs to come out from our castable, and they will do so through the interfacial transition zones, which are regions of high porosity that occurs in the boundary between aggregates and finer particles. And this region is a critical highway for moisture to come out. And the most important aspect is the bottleneck that is formed through the contact of solid particles. That will be the limiting factor for the kinetics of water removal. And so the question is how to bypass these bottlenecks. And we can do so by considering the connections of the already existing high permeability zones inside these materials. And this is where the fibers come in. The use of materials with high aspect ratio can lead to a connectivity of all these positions. However, if you do have fibers here, you probably won't have space for moisture to come. But connection is a process that occurs during the heat up that leads to the aperture of a bed for moisture to come out. But the question is how that happens. If you look in the literature, there are roughly two hypotheses that can try to explain this. And both hypotheses are supported by empirical observation. Let's think first on the first hypothesis here about the pressurized bed in melt of polymers formation. So we might think that during the heating up of the castable, the polypropylene fibers, for instance, which is a very common additive used in the industry, can actually undergo melting. And thanks to the combination of the pressurized water inside of it, you can form like a little straw or a path for the moisture to escape. And that correlates quite well with the measurements of airflow rate that were made at different temperatures in an equipment developed here in our lab. We could see that indeed the largest amount of permeability increase occurs in the temperature of melting of polypropylene, which was around 160 and 165 degrees Celsius. So it makes sense. It could be a possible explanation. But we have issues, and we have three main issues for this hypothesis. The first challenge is that if you think about the behavior of the physical polymer fiber, you will see that in fact we have a large increase of the occupied volume by the fiber itself. As we know, materials will try to expand thanks to the thermal expansion. But more than that, we need to account that polypropylene is a semi-crystalline material. So there is a large portion of the molecules that are really well packed in crystalline matter that goes under melting, leading to a high amount of expansion. And if the polymer is expanding, how can you actually create a channel inside of it? There will be quite challenging to open this kind of channels. The second issue here is that when we analyze the behavior of moisture removal from refractory casticles, there is a very significant effect we need to account, which is called moisture clogging phenomenon. This phenomenon occurs when you have moisture that condensates at colder regions of your material, and the liquid water itself will actually behave as an obstacle for the moisture to come out because of the high viscosity of the material. And if water itself already can act as a barrier, you can imagine that polypropylene and melted polypropylene, which has orders of magnitude higher viscosity, would actually be an even larger barrier for moisture flow. And finally, the third point is that the pressure that is developed from the moisture evaporation is not that high in comparison to the pressure that you would need to actually move or push this polymer aside. Just for a reference, when we're talking about injection molding of polypropylene pieces, we are talking about pressures in the range of 100 megapascals. So 20 times more what we would see at large temperatures of 250 degrees Celsius for the Newtonian equation for the vapor pressure of water molecules. So that can be a troubling aspect to consider. The second hypothesis here then would be the microcracking formation due to the thermal expansion mismatch. As we already saw, the tendency for fibers is to expand in their radial direction. And there are some micrographs in the literature that indicates the opening of radial cracks around the fibers, and which makes sense. If you compare the thermal expansion values for the different kind of polymers with a cement base, on this case talking about Portland cement materials, we would see that indeed we have a large variation between this kind of behavior. But on these kind of studies, the measurement of this property ignores, for instance, the creep of the system on the fiber itself. I think our colleagues here could learn a little bit with us working with refractories that creep is an important aspect. And then what we're seeing here is not thermal expansion itself, but a combination of thermal strengths and also kind of creep strength. But another aspect is that all these kind of analysis, they're a posteriori analysis. So we do not know exactly when those micro cracks around the fibers were formed during the material heating. So this is another challenge for this kind of hypothesis. And finally, if we consider the temperature evolution of the properties of polypropylene, we see that indeed, at the peak of thermal expansion coefficient increase, we do have a decrease of the young modules of the material because actually it's melting. So with all that said, what we can assess from this, from analytical tools to understand the possibility of microcracking. So the objective of this study is to investigate the elastic properties and thermal expansion behavior of polymer fibers and try to estimate the thermomechanical stresses in situ at the interface between the matrix and the fiber and provide a sensitive analysis for this kind of parameters to see how these different properties will impact the stresses that are generated. Because if this indeed is effect of microcrack is an important one for permeability, then we want to control this kind of interface behavior and to actually promote high permeability. And finally, with this information, as this showed us, try to create a similar framework, but now for selecting and design fibers for optimal drying performance. For this analysis, we will rely on the experimental measurements in the literature based on what they call the PET test: pressure, volume, and temperature variations, which can be done on a quite simple equipment with just a die and a piston in which you mount a portion of polycrystalline materials, and with that we can say how it levels during the temperature evolution. And with this information, we can now consider two important topics. The key takeaways here is that closer to the melting point, there is an increase of specific volume, as we mentioned, due to the melting of the semi-crystalline fraction, and also this crystalline will impact the expansion. And with that, this kind of information can be used on analytical models that can predict the radial displacement of this interface. And this radial displacement can be converted onto a strain, and with that, we can calculate the thermal stresses as well, originated by this mismatch of coefficient of thermal expansion. For our sensitivity analysis, we will use those equations to actually predict what changes with different temperature levels. We are also going to see the effect of fiber radius, the young modules of both the fiber and the matrix, based on variations of somewhat representative values for this kind of materials, and also for the thermal expansion coefficient of those two phases. We are going to assume constant +1 ratio for the fiber and the matrix, and with those informations, infer the effect of the sensitivity of the system. Starting with the results, when we look for different polymers that are adopted in the literature, we can compare the behavior of low-density polyethylene, propylene, polyethylene, polyamide, and ultra-high molecular weight polyethylene. All these different kind of polymers will show different melting points, which in fact would be related to different behaviors of permeability enhancement on a given castle. But most importantly, we want from this kind of curves draw what happens with the tangential stress that we calculated using those kind of analytical tools. And here I'm showing the evolution as a function of temperature increase, and on the right side I'm showing literature results happens with particles and concrete with different kind of polymers here. So we can have somewhat of one-by-one comparison of what is happening. And I would like to first pay attention to the three most common polymers used on this kind of analysis. We can think about the polypropylene as one that shows a high tangential stress and which leads to the avoidance of cracks of samples that were tested on explosive spalling furnace testing equipment. That behavior of resistance to explosive spalling was also seen to the polyamide polymer itself. But when we see for the low linear density polyethylene, we see that what happened was a crack on the experimental test, which correlated to one of the lowest amounts of tangential stress. So indeed, there is a correlation. We cannot attest here any kind of causation, but at least there is correlation between this information. And if we go further here by considering what is the behavior of ultra-high molecular weight polyethylene, it wasn't as effective as an additive for preventing exfoliating, and also at the temperature of interest led to a very small tangential stress that perhaps when it started to increase was already too late, thanks to the explosive spalling that already took place. And finally, there was also the behavior of polyethylene, which showed high tangential stress, but only for higher temperatures, which would lead to this behavior of exposures that is shown here on the stage. Okay, so we see that there is a correlation. We are on the works of trying to provide final assessment of if it is indeed a thermal crack, one of the explanations for the permeability additive behavior. But now let's try to just see what we can change by comparing the different parameters. And as expected, we see that as we increase the temperature of this kind of analysis, there is an increase of the tangential stresses around the fibers, which is represented here on these circles here on the middle, and then the tangential stress increases with this temperature effect. The fiber radius effect doesn't change the magnitude, but only the range of the material that is under these kind of high stresses. The young modules for the fibers create a very important behavior, and this, as you can see here, specifically showing that if we increase these young modules, we are translating more this constrained motion of fibers to stresses in the segment matrix, and also we can see how that impacts on the coefficient of thermal expansion. So basically here, the most important aspect is this coefficient of thermal expansion of the fiber itself. The castable behavior here on the matrix doesn't change that much the final behavior as expected. And so if we plot all this data, then we can see how well the behavior, how important it is the behavior of the fiber properties, really like relating to the young modules and also the thermal expansion coefficient. And finally, the conclusions for this study, the polymer specific volume increases upon heating. This is an important fact that we needed to account in trying to explain the observed behavior. And there is also a mismatch of the thermal expansion in comparison between the fibers and the refractory castable matrix. And the most intense mismatch occurs during the fiber melting, resulting on the high temperature stresses in the castable matrix that could be correlated to the formation of cracks that would explain the expansion, the permeability increase. And this complex behavior is what we are trying to assess nowadays with our current developments. And with that, just like to say thank you, but after that, also to just give a framework of what we're trying to do right now for the current work. We are performing neutron and X-ray tomography on thicker fibers for direct visualization, and this is a preliminary result that we just started to treat right now. I was back 1 month ago in France conducting this kind of experiments, and I will just give you guys a little spoiler. And there seems to have a couple effect of both thermomechanical expansion, but also we can see that the polymers they flow inside the cast. So indeed, perhaps that more than one or the other, maybe what you're seeing here is a combination of effects. And also we are trying to collaborate with the Brazilian Synchrotron Laboratory National Lab for an in situ drying equipment for high resolution to actually work with the samples and fibers which have the same thermal expansion than the same thickness than the ones used in the industry. And also we are performing a phase field model to actually try to see the behavior of the microcracks that we develop to answer indeed if those kind of stresses would lead to the tangential cracks we observe. With that said, thank you very much for attention.
We have time for questions. We have one question. I know when it works. It's fine. My question is, what value of elastic modulus are you using next to the melting of the fiber? How do you have this information? How do you measure this?
We are using the storage modules as one of the information for this kind of analysis. So when we take, for instance, this kind of plots, we go for dynamic analysis. There is like a light of temperature measurements of young modules in situ around the melting point. So to try to achieve that, we use this kind of information for dynamic tests for the young modules. And then at the melting point, we just assume the constant value. So for sure, in this kind of case, we would need to actually perform a multi-physics analysis. So we would need to consider phase transformation and also perhaps see if in the melt we could actually capture the flow of this melt in the porous medium. But that is still like something for future works. For the moment, we are assuming perfect elastic material behavior and also just trying to see not exactly the precise final value, but in the order of magnitude of what happens inside of it.
Thank you. Although the methodology has been carried out very subversive, instead about the flowing of the melting fire. You think that it's a combination due to the viscosity and the internal pressure, or one than the other?
I would say that it's a combination of both those aspects because this is also another important aspect. When we take into consideration this kind of resins here, obtained with the high temperature thermometer that was about here, we're only considering the overall behavior of the whole sample. So we're considering like a thick disc of 1 inch by 50 millimeters or 55 millimeters. And this kind of material occurs in an almost homogeneous temperature profile. Thus, what we see is this kind of not directly linear, but monotonic behavior for the permeability. But what happens inside the castable material during the drying was studied during my PhD using neutron tomography, was that in the material itself, we do not have this kind of homogeneous behavior of only high and increasing permeability. What we see on the drying front is that it can start to increase its velocity, but then it can even decrease the velocity thanks to the formation of moisture clogging all of these complex phenomena. So perhaps what is happening is the combination of the melting and flowing of the polymer, but also the microcracking itself. This is what we are at least preliminarily thinking that happens in these systems.
Thank you very much again for the presentation. We will move to the next presentation. Dr. Daniel Z. That's going to present our friendly binder system for MgO-Crecyclates obtain legal rates.
Thank you very much, Professor, for your introduction, and also from my side, a very big thank you for to be here. And from my side, it was a big wish to visit you in Brazil. So it's fulfilled. So I'm happy very much. So my today's talk is about the friendly binder system for MgO-C recyclates containing later bricks. And I have to admit, this is not my work, which I will present you. Then to colleagues of mine, Mr. Murilo H and Mr. Till Stadtmüller. So please give it that way that I'm just talking for the both. So short introduction to the topic. MgO-Cs are dominating refractory bricks for iron and steel production in the blast furnace or in direct using, and also in the electric arc furnace. And in a global refractory production is estimated around 35 to 40 million tons of refractory MgO-C. And from this amount, approximately 70% is in the iron and steel industry. That means that we have 28 million tons of spent refractory generated worldwide annually. And you see, this is a very, very big potential which you should use and try to search for alternatives and how we can lend in good topics and with increasing research in fields where we can adopt them. So basically, the MgO-C refractories are using pitch and phenolic resin to get a C1, and we have here a problem that these compounds affecting humans and environment. So these both topics we should go on and try to search for some solutions for the recycling and also to try to change this pitch and phenolic resin modes to alternative environmental friendly binder systems. And also, due to these both, we are contributing to a lower CO2 emission by utilizing spent refractories, and we are developing eco-friendly binders to emit the carbon balance. So, for the first point, let's see what we can say if we are using plates. And you see in this slide that we also could avoid that these recyclates land in landfill waste. So moreover, we can recycle them, and these raw materials which are conservating in this system to be newly used. And if we are looking at the magnesite and the type, the furnace, for example, rotary kiln furnace, then we see that during the decarbonization, we have
0.99, so almost 1 ton CO2 emission per ton of MgO. And the direct calcination is also 0.35 tons per ton of MgO. So it's a very big amount of CO2 emission, which we can avoid if we are using recyclates. How they look like on this side, you can see the big difference. Where I have used MgO looks like as on the left-hand side, where we have low impurities, high density, and the crystal size of approximately 80 micrometer. In comparison to that, MgO-C recyclate, which already has 10% of carbon inside, has a very high amount of pores and a crystal size of approximately 73 micrometer. Also, it has a lower calcium oxide content, which influences then the calcium CS ratio in the MgO-C recyclates. Some preliminary works, have been done, and it was a DFG transfer project with DEV and boron, today the refractory boron. And in this transfer project, 3 were lined with in the slag zone here with recyclates containing refractory bricks in the upper and in the lower slag zone. And as we can see here on the left-hand side, you see that they withstand many cycles, so they had promising results from these transfer projects. Also, at our place, we introduced steel blocks. We analyzed steel blocks from some immersion tests in the steel casting simulator, where we used different kind of bricks containing 0 amount of recyclates up to 100% of recyclates. And in this table, I would like to only show 2 results. Firstly, with 0 recyclates, we received a total amount of 6,000 inclusions. From this 6,000 inclusions, a very high amount of aluminum oxide inclusions, which we call hard inclusions. These hard inclusions are responsible or could be responsible for some damages if they are agglomerate. So our goal is, and our result shows in the last several years that as less inclusion, aluminum oxide inclusions we do have in the system, as the best is for the steel and against the agglomeration of these inclusions becoming critical agglomerate and then leading to a huge defect in the steel. And if we are using the 50 to 50 recyclates and fresh material, we could reduce, or we are seeing that we are reducing the aluminum oxide inclusions and also the overall beneficial amount. So the potential of sustainable binders for the carbon refractories is the second big question nowadays. How we can change the resin and adapt something new, which is less toxic, which is renewable, which can protect the environment. So we try to search for alternatives, and coal again, lignin,
and fructose and tannin are suitable materials for this purpose. So my colleagues started to test these in combination and also alone in the MgO-C system, where they were introducing these kind of binders, mix them with fresh or with recyclates and fresh materials. Then these mixtures were pressed universally with 150 megapascal to cylinders with a diameter of 50 centimeters. The resin binders as a reference were cured after the typical curing process up to 220 degrees Celsius with some dwell times in between. And the novel sustainable binders were only heated with short ram in between at 90 degrees, approximately 90 degrees Celsius, and that they were dry at 300 degrees C. And after all, the samples were cooked at 1000 or 1300 degrees Celsius, respectively, and these results I will show you now in the upcoming slides. Please give attention that the results are either 1000 or 1300 degrees Celsius cooked, and for the lignin collagen batch series, it's differently, and also for fructose collagen. So we see it now as one temperature. Do not make if I'm sorry. So I will come to that later. So liquid collagen batches can be seen in this slide. Here we do have the reference sample on the first row, and then we have called LC50, the recyclates and the fresh material. So every time where the LC is 0, is no recycled material is inside. Where the number is 50, then it's 50% recyclates, 50% fused is introduced in the mixture. For the combination, lignin and collagen, lignin 2.4 and collagen 0.6% is used. And for these combinations, we used the ionized water. Later on, we added some antioxidant additives. And the last batch, the colleague of mine was trying to change the ionized water into ethylene-like. The results can be seen in this slide, and as you can see, we have the reference batch very high gold crushing strength, approximately 30 megapascal, and open positive from about 10%. If we are using 50 to 50 fresh material and recyclate, we receive a very combination of lignin and collagen. Then we receive a very huge drop of the cold crushing strength and receiving something around 4 megapascal strength. And due to the addition of 50% recyclates, we increase the open porosity highly. So approximately 19%. If we are adding to the 0 recyclates composition some antioxidant additives with the lignin and collagen,
we see that we are increasing the cold crushing strength to 11 megapascal. That means that the recyclase has huge influence on the microstructure and also on the strength of the sample. Hereby, if we are adding the antioxidants, we can decrease a little bit the open porosity. If we are adding to this mixture the recyclates, as I already told, we are decreasing the cold crushing strength, increasing once again the porosity, and these mixtures were made with water. If we are changing the water, suddenly we have some quite different results, some positive results, because we are increasing the cold crushing strength up to 17 megapascal, and also the open porosity could decrease with this change. So my colleagues were thinking about this combination has an influence on the whole microstructure, and therefore they tried to separately see the influence of the collagen and the lignin with ethylene glycol, and these mixtures were already trimmed for an industrial introduction and to see if we can scale up later on the samples. So the results showed that the combination of the collagen and the ethylene glycol and the lignin and the ethylene glycol leads to different results for the favor of the collagen, because the collagen can be very good compared with the resin, so with the reference sample. Here, I need to say that these are splitting tensile strengths and not the cold crushing strengths. Well, as you can see here, we have only a slight drop of the tensile strengths if we are introducing the collagen instead of the resin. But we have a huge loss if we are introducing lignin instead of the resin. The refractoriness on the load is also displaying this kind of difference, and we see that very good and very comparable results can be seen if you are introducing the collagen with the ethylene glycol, and both of the curves see here. Yeah, okay. So these curves, so they are very similar to each other. Nobody could say that which one is the reference. The XRD result shows also that the collagen displays increased amorphous carbon amount after the test. So we can conclude that the collagen samples are stable up to 1600 degrees Celsius and superior to lignin as a binder. I already talked about the scale-up issues and why the composition was made up to 7 millimeter porous grade. These mixtures, what we were talking about before, were then sent to the Refra technique, and they made big blocks from the mixture. And after some time, I think after cooking, after hardening, sorry. Yeah, after hardening, these bricks displayed cracks, and these were then a big question why these cracks occur and what can we do to avoid them. Therefore, collagen and also the lignin was cooked separately and also was measured with RTG and iron. So we see that above 200 degrees Celsius, the collagen peptides chain start cross-linking, but also it start thermally decomposes and we measuring gas release and foam formation in case of the collagen. So to optimize these expansion problems and try to avoid it, the colleague started to make a collagen lignin combination from 3 to 2 and from 0 to 1 lignin collagen addition. And if we are looking at the volume change, if in these contexts, we see that with increasing lignin content, we are decreasing the volume change in the system. So the optimum was found with the combination 2% of collagen content and 1% of lignin content. If you are then having a short look also on the lignin during the cooking process, we see that the lignin shows no cross-linking and undergoes a thermal decomposition combined by the glass release. So, furthermore, there would be maybe an addition how to work against the expansion, and therefore the colleague of mine, changed the graphite addition from the original 10% of flake graphite to 5 and 5 flake graphite and fine graphite, and you can see the results here. This kind of change resulted in a very good volume change. So fine graphite particles improve the gas release and improves to counteracts the anisotropic thermal expansion of the NFL graphite. So I try to catch up and be a little bit quicker. This is the work of Mr. Murilo H, who was dealing with the fructose collagen and tannin binder system. And here needs to be said that the fructose which we are applied is the solution, 70% fructose and 30% of water is introduced if we are introducing a syrup of 2.4%. He chose also this kind of fructose collagen and fructose tannin combination of 2.4% and 0.6 to come up to 3% overall fiber addition. And here you can see the first results from these, where we receiving cold crushing strengths of approximately 27 megapascal for the fructose collagen and 26 for the fructose tannin. And if you're comparing this one with the resin binder, we see that we are very nearby the cold crushing strength, and the open porosity is slightly higher, with approximately 14%. If we then adding the MgO-C recyclates to this system, and changing nothing else, then we are receiving slightly lower strength and slightly higher open porosity, which we are also know from the other results from Mr. Schramm. Finally, Mr. added citric acid to this mixture, and the results shows an increase. So he reached to increase the cold crushing strength and also to have similar porosities. But this kind of citric acid introduction was a positive effect on the system using Crecyclates. So this is the main message from the addition, that although we are using Crecyclates, we can improve the cold compression strength. The refractoriness under load was also tested with and without citric acid addition. And as you can see here, the results showed that with the citric acid in the introduction, an increased T01 could be reached for the samples. And the same he did also, with the collagen. And here we can say that the citric acid addition is not so favorable for this kind of composition. Without citric acid, the refractoriness under load is very. Finally, he made some steel casting simulator tests with these positions, where we were melting approximately 40 kilograms of steel, 42 chromoles for steel in an argon atmosphere. We are oxidizing and deoxidizing the steel to generate aluminum oxide inclusions. And these samples were immersed for 30 minutes at 1600 degrees Celsius in the steel mill, as you can see here. And the first results, which were very, very unusual, is that all around the samples, residues of steel could be seen, which we did not observe until these tests. And these thin layers then were analyzed a little bit deeper. And we see that we are having some dendrite structures aggregating, which leads to the results that we have a carbon thermal reduction at high temperatures. And these dendrite structures are forming near to the surface of the immersed sample. Here you can see also some SEM analysis and ADAX analysis from these samples and from these dendrite-like structures, and we see that at the D and E here we are having increased amount of aluminum oxide and MgO. Also, the mapping shows us that these areas, aluminium, MgO, and oxygen is can be measured. So to sum up the project, collagen, lignin, tannin, and fructose represent friendly binder systems, possible binder system for MgO-C with 50% Crecyclates. Collagen samples with methylene glycol are stable up to 1600 degrees Celsius and superior to lignin as a binder, but they still have high porosity, which should be decrease. Fructose and fructose coloring binder system results in higher crushing strength and lower porosity, almost near to the resin merchant sample. Citric acid further enhance mechanical properties, and the industry standard format bricks can be pressed crack-free with the change of the composition and with the change of the graphite in indeed and the fine graphite and the natural flake fire. And finally, as before said, a thin layer of steel formation with a dense structure areas were observed in contact with the steel for these samples. With that, I would like to thank the DFG Deutsche Forschungsgemeinschaft for founding this project and for you your attention. And if there are any questions, I hopefully can answer. Please feel free to ask.
Because the introduction shows some results with like the counting of the inclusions.
Yeah.
And this was from aspects analysis.
Yes.
And afterwards, we also conducted some experiments on these two gas simulator. So did you also run this kind of thing of analysis for the inclusions in the models too, not just like on the surface of the
Surely they did, but the results are not familiar for me, so I cannot answer where we are looking with the exclusions. But I do think that in some months or weeks they will have a report about this. And if you have further interest, you can keep contact and I can show you the results. My phone that's muted from the top. Sorry. CIS calendar spot.
You tested in beginning like sugars. Where did you have this idea of using this type of products to test as binder?
There, so I know that fructose was already tested in the late 80s, I think 90s. So and they had good results, but there were no further interest for a deep research. And basically, if you are trying to search for some alternatives, there are I think one or two questions which you need to answer. Do we have some additives which are having a high carbon yield? So they are delivering us carbon, and how is the stability of the carbon residues? And already, if the first question can be answered with yes, it has a very high carbon yield, then you should test, or we should test these additives as a potential binder system.
Thank you.
Yeah.
Thank you very much again. Now, final presentation.
I'm purpose having this one to try something in the discussion.
Operators open the auto and
So it's not.
So do you hear me?
Yes.
Yes. Can you hear me?
Yes.
It's fine.
Yes.
Perhaps according to the new Yes, I can hear you. Yes, according to the new approach with the binders, we have to think always about never. We will never have the same properties as short pitch systems. So we have some problems according to the total porosity. You see this, especially also when recyclates are added. And I believe we are in very good approach because first of all, yes, but of course we are in a very good approach because strengths are in the same level, especially in combination with the citric acid, due to the cross-linking. And if the inclusions, so Florian Kerber in terms of this group has also measured the inclusion distribution, the shift of the, or we see a change of the chemistry of the inclusions, the manganese silicates, which is in a positive means. Of course, such systems need to be tested in a small scale before talking more according to a potential application in the future. That's why we have cooperation with industrials, steel plants, as well as refractory companies in terms of the gradient collect, which support the PhD students, so that we come always closer to the application, understanding better the application. Thank you very much.
Thank you. Now continue. We go to the final presentation by Murilo dos Santos, that is going to present short sampling in sintering. First, to look into our calcium, zinc, refractory castables, and alloys.
That's it. Thank you, Professor. Thank you, all of you, for this great event, and also thank you to the audience that is been following all these lectures. As Professor mentioned, I'm going to discuss a little bit about the transient liquid sintering, not only for the AZS system, but also to other ones, in order to try to explain what kind of methodology we are developing here to explore this kind of ideas, and especially because when we talk about transient liquid sintering, the main goal here is to reduce or to promote the fast sintering of the refractory ceramics by reducing the defined temperature, or to making the sintering process faster in most of the applications of refractories. So this is a project that has a lot of students working on it, and the idea here will be showing you mainly three aspects of this project. So first, we're going to revise and explore a little bit of the alumina boron system. Then we will, since this is like a pretty simple system compared to the other one, we will see how to visualize and to understand these more complex systems and more complex mixed structures. And then at the end, we're going to look a little bit of the first results we got for the AZS system and its additives. And in case here, the transient liquid additives. So starting with the aluminum boron system, as I mentioned, the idea of using this technique is to reduce the temperature for firing these refractories. And we can see in the literature that the use of boron, the many different sources of boron, is one of the strategies to foster this sintering process. I didn't know that boron was so problematic for the steel making. So maybe the idea of developing this methodology could even add some additional positive effects of this study. So when we look, for example, in this paper that was done here in our group. We can see, for example, and here we're gonna mainly see some experimental results of the elastic modulus as a function of temperature, because this is one of the techniques that we consider that is good to see these faster sintering, as when we sinter our material, what we see is an increase of this elastic modulus. And in the case, there's several results here, but I will mainly focus on the ones that have this boron addition. And we see that approximately at 600 degrees C, we can already see some increase of the elastic modulus. And when we heat these castables, we don't see any changes in the elastic modulus. This is the results here in the second plot. So what we see is that in the first heating, there is some liquid in the middle structure that helps the sintering process. And this liquid reacts with the matrix or with the other components of the castable. And then in the second heating, these phases are already stable and they don't show any changes in the elastic modulus. So this is one of the evidence that we have, and we're trying to apply the same concepts to other and more complex systems. And even though we verify this kind of results for this alumina boron system, if we look, for example, to the phase diagram of these two components that was generated by Falsetti, and there's just these small additions of boron. And if we check in Falsetti, we're going to be in this dashed line here, and the predictions doesn't show any formation of liquid. If we take our composition, that is like just one small amount of boron, and what we have here, just like this stable phase and the very refractory, the phases with higher refractoriness. And even though if we increase the amount of boron, let's say we start to work with a composition of 10% of boron oxide, we are still in the same field of the phase diagram. So no liquid is expected in this composition. But if we look at the horizontal line of this composition, let's say at 1500 degrees C, and we can expect that these components are segregated in the microstructure. Of course, there is like a small portion of combination of these two components that will form liquid. In the case of the diagram here, it's quite for this kind of system, it's quite easy to see that. And even for this composition, if we take it and as Falsetti to predict what's going to happen, it will show us that 70% of the phase will be these aluminate borate aluminates, and 25% will be carbon. So another way to visualize the same effect, and that's what we are trying to develop here, is to overcome this limitation of Falsetti that only treat the systems as a superbalance. And as I mentioned, Falsetti will not consider any diffusion between the components in the microstructure, and will only minimize the heat-free energy of these components and show the phase they were formed. But we know that microstructures of real products and real materials have a much more heterogeneous condition. And in order to advance a little bit this kind of analysis, we are trying to account this heterogeneity in our developments. So let's say we can, for example, create a mesh in our microstructure. This is like a hypothetical one, but we can like divide all the microstructure into small portions and small elements. And let's say, for example, we have two single elements, one of alumina and the other one of boron oxide. And we are here at 1500 degrees C as a condition. We can then take these two elements and start to mix them. So the interfacial elements between these two initial elements will mix, and they will have half of the content of the initial element. And after that, in a third step, we split this mixed element between the two parents element. And now what we have is a resulted element with a little different composition of the initial elements that counts for this mixing of the two components. And of course, these are only two elements, but they are in a whole mesh. So imagine that all the elements will mix with all the neighboring elements. And the result is a known finite diffusion of these components in this microstructure. And what are the outcomes that we can get from this analysis? This idea is also reported in the literature, and it's called cellular automata. It's a very simple way to reproduce the diffusion process in a simpler manner, where we can approximate the fixed second law using this finite difference method. And of course, we can estimate the diffusion coefficient for these components. But of course, we won't be able to assume several different diffusion coefficients only with this model. But we are now able to at least consider that it's not finite. It has a little effect of time on this mixture, and different from what Falsetti already considers. Again, just to highlight better what we're doing now. So let's say we have like these two different blocks of aluminum and boron oxide, and they are in contact with each other. So the whole the composition of the whole system is 50% boron oxide and 50% aluminum. So we divide all this structure into small elements, and we start to mix the elements, then the top element and the right element and all the neighboring ones. And we do that in several steps. And what we're going to see is as soon as we start to iterate along this mixture, the initial composition will tend to the final composition. So locally, we have distinction between boron and aluminum. But after, let's say, 300 iterations, we're going to have the homogeneous composition that was what Falsetti considered when he analyzed punctually each one of these situations. So there are, of course, some assumptions in this model. There is a uniform diffusion coefficient for all these species in this mixture. It's isotropic. There's no distinction between the directions in the system. Locally, there's an instantaneous mixing, similar as what Falsetti does. And there's no source or sink terms. And at the boundaries of our system, there's no mass transfer or any other diffusion. So if we get back to the aluminum boron microstructure, and this is also hypothetical microstructure, but we use that to illustrate what we're trying to do. So the global composition stays 10% boron oxide and 9% aluminum, but locally we have 100% aluminum in the matrix and some, let's say, aggregates of boron oxide. And if we look to the initial composition, we have 100% of boron oxide at the dots and no boron oxide at the matrix, and the opposite for the aluminum. And as I mentioned, after mixing this microstructure 300 times, what we get is the composition of aluminum. The overall composition tends to 90%, and the overall boron composition tends to 10%. But all homogeneous as considered by the Falsetti calculations. If we take all these steps and ask Falsetti to calculate the phase generated at each step, initially, of course, as boron oxide melts at 4,500, 450 degrees C, initially there is already liquid at 1,500 degrees C in the regions where boron oxide is located. We don't have initially any complex boron aluminates, and the matrix is mainly corundum and aluminum. So as soon as we start to see what's evolving in its microstructure. And the liquid generated initially spreads out, and there's the initial precipitation of the boron aluminates, and the alumina is being consumed to form these aluminates. So, as I mentioned, initially we don't have the aluminate, the boron aluminates, and we have just 10% of liquid. As soon as we start to mix this microstructure, this liquid disappear, and the precipitation of this boron aluminates reach the same value that Falsetti predicted if you only give it this composition. So that's the main concept. The idea here was to apply the same thing for a much more complex system. As I mentioned, we could already see that mixing in the phase diagram of this binary system as we look into that horizontal line. But now when we have like 3 or more components, it's much more difficult to see what's happening. So back to some experimental results that has been motivating us to investigate the use of zinc oxide in that. As Otávio mentioned as well, I think when the group started to work with zinc oxide, there was several open questions, and one of them led to your study and others to this one. For the same for castables that are made with these 4 components. When we evaluate the elastic models, well, we see something similar as we've seen for the boron system or alumina system. And there is like this heat chain that happens in much lower temperatures. And we are trying to investigate if this is also the case of formation of a liquid or a transient phase during this stage. And checking Falsetti as well. The same castable here is like 50% MgO and 50% zinc oxide spine. Smell. And if you check that in Falsetti, there's also no liquid. If you check this composition. So let's see if we apply the same methodology we've done for the boron system, if there will be something that wasn't predicted before. Again, it's just a hypothetical microstructure. We considered 3 calcium aluminate cement aggregates, 2 zinc-side aggregates, an alumina spinal matrix, and a aggregate of aluminum, just to create these differential local compositions. And with the aspect to predict what happens in this microstructure, what we're going to see is there are some moments where there is some liquid generated, but this liquid just spread out and mixed with the other components. So that was the first indicative that this system also could be undergoing same mechanisms as the boron alumina one. But that's not the end yet. We are still investigating in more depth, and the idea is to use this approach to find and discover other potential additives. And not only the liquid is here we were seeing only the liquid, but if you look to all the phases that Falsetti predict for this system, there are different phases. And the liquid is the one here, but other transient phases occurs as properly this inside, or even the MgO, the solid MgO, it also appears and disappears. We can see the transition from Ca to Ca2, the spinal dynamic in the system as well. Just to highlight that there's only not liquid, you could have even other phases in this kind of analysis. And some initial results of experimental evaluation of this system. What we are comparing here in these 2 graphs is the system with also aluminate cement and the one with hydratable aluminum. So we're trying to remove calcium from the system here. And what we see is that when calcium is present, we see this first increase and decrease of the elastic modulus, but when calcium is not present, that doesn't happen. So we believe that calcium is important and plays a role on this dynamic. And this is like trying to validate this strategy and the methodology. And if we can ensure that this is the case, we could use Falsetti to find these potential additives and potential sintering, lower sintering additives. So just a quick look also to the strategy to find these additives. We first started to work with only these 4 components, but then as we were investigating potential additives, we decided to add also silica, and we were working with 5 different oxides. And we explored with, like, say, all combinations of 5% of each one of these oxides, which led to more than 10,000 combinations. And we were checking quite something similar what you've done, which one of the components show the formation of liquid at lower temperatures. So at 1300 degrees C, there were almost 200 candidates that generated 100% liquid at this temperature. And they're all being displayed here. Some comments there, some of them that don't have alumina, some of them don't have magnesium, but most of them have silicon. And since we did not want to work with silica at the first moment, we were mainly focusing on this part here of the candidates, where there were no silica and just zinc oxide, calcium, and aluminum. So these are the promising low sintering additives at the beginning. But here we were at 1300 degrees C, so we decided to increase a little bit more the temperature to 1200 degrees C, and then we end up with almost 1 candidate in this condition that we are evaluating with no silicon. And when we actually check the composition of this promising additive, we then compared with the ternary diagram for the alumina calcium zinc oxide, and actually pretty close to the ternary and the eutectic point of this diagram, which has a melting temperature of approximately 1100 degrees C, and the composition of this point is approximately the one shown that is box over there. So 40% of alumina, 35 of calcium, and 22 of zinc oxide. The idea now is to go to the lab and try to produce these additives and try to use them in the castables to see if we can get the same effects as we've seen earlier. Unfortunately, we don't have time, and these results are ongoing now, but it is to create this setup to produce this additive, take part of this additive and mix it in a castable, and do the elastic models and check if we can find the same behavior that we were expecting initially. And of course, there's no such thing as free lunch, as I always mentioned. We need to understand better what's happening and create even more experiments to verify that this is the case, using other different techniques to check exactly what's going on in our castables to see if the methodology is reliable, so we can then even combine with other databases to identify these potential candidates and use them for using and mixing them in castables to reduce the total the final sintering temperatures and reduce the energy consumption required to produce such castables. This is working in progress, and hopefully in the future we can show you all the results we got from these developments. And that was it for today. Thank you.
Thank you, Marcos, for speaking out for the issue. So pretty close to the final time, but we still have time for the question for the final words and controls and words. Tired. Okay, thank you very much then. I'm just going to finalize and change it. Thank you very much for this interesting meeting that we had. I would like to thank you from us Aneziris for the initiative for this encounter. I hope you're there seeing it. And where am I? Also, okay. And I think that this morning we had different views, all of them in shaping our future, and the future has a color, it's green. And we have seen from the beginning the whole aspect of the project that it has been carried out in Freiberg under the leadership of Professor Aneziris. And we saw different views, how we can save energy, how we can recyclate materials. With a talk by Otávio, we have seen that we can save energy by producing some advanced insulators, but without using fibers, and perhaps in the future to put in contact with molten steel, because due to the smaller size, perhaps we can avoid filtration. And afterwards, we have seen by Alexander the thermomechanical characterization of recyclates of MgO-Crecyclates, and we see very promising results that we look forward for them in the near future. Afterwards, we have seen resultado that is a computer simulation to predict the slag foam behavior. It's another way of saving energy and protect the refractory. As you know, that the future of the steel goes to an furnace. Then Rufus showed us how to produce self-glazed components and boron-free. And also a different aspect of green refractories that it's also very promising. Also, by Murilo, we have seen on one aspect of drying that it's very important since we know that nowadays everybody is thinking about castable line steel ladles by castables. Then the key aspect of saving time and performance, it goes through a proper drying of this castable. Then Daniel showed how to investigate friendly binders. That is also quite interesting because although it's a big challenge, and there are quite a lot of results in the history of the Freiberg group, and we believe that soon you're going to get something very close. And finally, Mateus showed how you can use computing operation to speed up the sintering, the sinterability of the ceramics, and to decrease the temperature in order also to save energy without damaging the performance. Then I think that it was quite different views of the same problems, and I'm quite sure that there are many others that we didn't show here, but around the world everybody is thinking about this problem, and why not refractories to be in the same tube? I think that finally, I would like to say that although politics nowadays are building walls and inhibiting interaction, science cannot fall in that trap. Now we need to be close, we need to interact, we need to break barriers, otherwise we are going backwards. Then I thank you again, all of you, Daniel, Patrick, Alexander, Vasileios, that came to visit us, and we hope that it's not going to be an opportunity to interact, but actually something that would speed up our interaction. I think that both groups are in the same tune and in the leadership of the research in this area. And I believe that joining forces it could achieve much more scientific and technological results. That, Professor Aneziris, thank you very much for promoting this interaction, and the final word is yours.
To take some time because of it later.
I would like you very, very much for all the work. And I believe in the future we will have a bigger amount of our PhD students, also some women. Because we have very good women in Brazil, but also in our colleague in Germany. And perhaps this would be the second opportunity to come together. So thank you very much once again. And I would like also to thank the DFG for supporting our activities.
Thank you, and hope to meet everybody in Kirkendall, a much more nice place at the beach, talking about our times. Okay. Bye bye, and thank you very much for being with us.
See you. Bye bye.
Have a good dinner, and we're going to have a good lunch. Bye bye.
Bye
That's it.
bye. Bye bye.
Bye.